start recording because this part is important. So this mesh right here, since it's valid and closed, you can make slices through it, meaning if I grab a clipping plane and I kind of drag it up, the slices that are produced through it, the sections, are always going to be closed polylines, right? And since they are closed polylines, the computer will have information over what's inside and what's outside, right? If, for instance, delete mesh face, delete. If this, for instance, face is deleted here in the mesh, and it means it has a hole. And now if I were to slice it, you can see that it doesn't fill inside of the mesh, right? Because it treats it like it's two very thin shells, or rather one very thin shell. And that's simply because this part right here, when we're making a slice through this part, it's an open polysurface, meaning that there is no information over what's outside, what's inside. Remember when I said that the meshes need to be watertight, meaning don't have any holes? This is exactly what happens if you have holes, and it won't be able to slice it properly. So I'll come back here, fill in this hole, delete the clipping plane. This is a clean mesh, so we can export it. I will select my shape and I will export it as an STL. Cura or any other 3D printing software doesn't understand any other format other than STL, stereolithography, right? So I will select my shape, I will type in export, and I will just give it a name, my first print, and I will expand where it says save as type. I will expand that drop-down box and I'll just find STL, stereolithography. So STLs are, and just hit save and hit choose binary and hit OK. So STLs are the most bare bone, how do I explain it? For instance, if you export something as an OBJ or as 3DS or as even a Rhino format, if you export a mesh as a Rhino file, it contains more than just geometrical information. It contains textures, it contains UV normal information, it kind of carries together with it additional information. If you save something as an STL, that is just pure geometric information, nothing else, right? So STLs are the most bare bone, most simplistic formats that are out there. Back here, that's the STL. I wonder if I can, okay, it's compressed, so I can't show it to you. Doesn't matter. So this file was created, my first print.stl, right? To import it into Cura, all I need to do is just drag and drop it. Drag and drop it in. And now it's in Cura, right? Let me know if it works for everyone. How would you go about scale? About scale of what? You should save it in binary, because binary ACII might be problematic with not with Cura, but with other software packages. ACII might be problematic. Binary is the most simplistic. How would I go about? How would you go about scale? Yes, I've showed you. If you select your model and type in bounding box, right, and you scale on your model, then you can click 2 points of that model and type in what kind of dimension you want, right? So I'll just type in 10, right? So that's, now it becomes 1 centimeter long. You just scale it in Rhino. Before you, and you need to scale it before you give it thickness. Okay, so back here, that's our model. And I believe rotating and zooming in, zooming out, yeah, it's the same thing in Cura as it is in Rhino. So at least that part is simple. Let me go quickly through this setup. So first of all, you have your shape here, right? And you can see that some parts of it are red, while other parts are yellow or whatever color, right? But some parts are red. Those red parts are where it says that if I were to print this, it would be as if I'm printing on air, right? So I will need some sort of a support system for me to be able to print these parts. And that's fine. Usually with more fancy architectural models, you will always need supports. So that part is okay. Just know that the red parts are where it says that we are getting over the threshold of what I can print without any supports. In Cura, if I select my model here, I have options, right? So on the left-hand side, I have options to move it, right? So I can move it kind of around the build plate. Oh, by the way, speaking of build plate, this is your build plate, right? So this is the dimension of the 3D printer of how big of a model it can print. Right? If you go beyond your build plate, the model will have this kind of a, I don't know how to call it, zebra stripe pattern on it, meaning that it's not, you know, it goes beyond the build plate and it cannot be 3D printed. So you can move your model. You can scale your model in Cura as well. And here it gives you all, it gives you 3 dimensions in millimeters, and also it gives you percentage. Scale it in Rhino. Don't scale it in Cura unless you really need to, but you know, do it in a clean way. Scale it in Rhino. Then we have rotation. So for instance, let's say, you know, I'm looking at the model and I say, well, actually, maybe I want to print it like that. And I can do that, right? So I can just select the model, choose rotation, and then kind of drag the arcs and rotate it in any way I want. But honestly, this is the best the best positioning for this model, for it to be printed out. You always want to minimize the amount of areas which will need support. And also you want to maximize the surface area where the element is touching the build plate so that it doesn't peel off. So that's rotation. Then you have mirroring, but that's whatever. And you have per model settings, that's whatever. And you have support blocker. We will, you know, it's a bit more advanced. We will look into it during the actual course if there's a need for that. But right now, just care about move, scale, rotate, in this case. So that's the first part. Second part is what's happening here in the top, right? So you have different printers here to choose from. In this case, you will only have one printer, and that's fine. But if you have more profiles, then you can choose between different printers. For instance, at home, I have Tivo Tarantula printer, and I can choose between my profile of Tivo Tarantula and Prusa i3 Mark III. Okay. Then we have generic PLA. So this is material type here. And we will not be messing around with the material type for now. We will not be creating a new material type. That's fine as it is. And here on the right-hand side, we have settings, right? So if you click on it, this kind of a menu will pop up. And wait, maybe you see something like this. Is this something that you see? Okay. So this is these settings are for. I just clicked on the right-hand side menu here. So these settings are for children. It is basically very overly simplified and so on, and these settings are used for. I mean, this is not a joke. It's actually for children. These are used for like middle school classrooms where children in the middle school can slice up their duck models or whatever they're doing there. So in our case, we will be a little bit more advanced and we'll go for custom. So we'll choose custom settings. Let me minimize all of these. And here we have a bunch of different settings that we can change. So first of all, and I will be going through all of them. Keep in mind that most of the settings are still hidden from you, and the only way you can enable them is by clicking the gear icon. For instance, if I hover my mouse over quality box and I click on the gear icon, that pops up. All of the hidden settings that that it's not showing us are unticked, and the settings that it is showing us are ticked, right? Meaning that even when we go for a bit more advanced control, this is far from, it's definitely not showing all of it for us. Anyway, we will just pick and choose the parts that we need. So first of all, if you expand quality, you will see layer height. And I think it's the only setting that you will see for now. It's layer height. So layer height is something that, tell you what, let's click slice in the bottom. Just, click that slice button. And then right next to save to file, you will see in the bottom left corner or right corner, you will see preview. Click on that. All right. For people who are using the school's computers, it's a bit different. I do have a, oh, cool. a small break. The video processing is done for the webinar. Yay. For yesterday's webinar. Yay. So you'll be able to check out the new video. Anyway, where is it? Where is it? Where is it? Like that, like that. I'll just find the video for people who are using older version of Cura with the school's computers. I have it somewhere here. Where the heck is it? Cura settings, there we go. Shush, copy, paste, here you go. So with Cura, with older version of Cura, to be able to see how the sliced model will look like, you will go to the somewhat top right corner where it says probably model view or something like that. And you will choose layer view instead of model view. And then you'll be able to change the color scheme from from material to line type or something like that. But it's basically here in the top. Instead of model view, you choose layer view. And you should be good to go. With the new version of Cura, you just click on preview either here or here, and then you will see, probably you will see something like this, right? Is this something that you see? Okay, so this is useful because we can see the layer height and we can see this, how this form would look like if it's made out of layers, but we cannot see which line type is which. And I guess for this particular task, it's fine. But just to, yeah, I'll show you how to change the color scheme later on, and I'll explain what different colors do. So back to quality settings. Where it says layer height, it says 0.15 millimeters, at least for me. It says that. So here, the thickness of each layer that is making up the model is 0.15 millimeters, meaning that if I increase this number, the model will have less quality, but at the same time, it will require less layers, so it's going to print faster. So here, the whole model would be printed in 1 hour and 52 minutes. If I change the layer height to 0.3 millimeters, so twice as big, and click slice again. So you always need to click slice when you change something. You can see that the lines now are much thicker, but now it's going to do this model in 56 minutes rather than 1 hour and whatever it was, 1 hour 26 minutes or something like that. So it becomes faster. And there's always this kind of balance of speed versus quality. The rule of thumb for layer height with these kind of printers, it's you never go below 0.12 millimeters, 0.12 millimeters, you never go below that. Simply because if you choose something like 0.05 millimeters, it will not give you better quality, but instead it will just increase in print times drastically. The nozzle is indeed 0.4 millimeters, but it's the radius of the nozzle, right? So the nozzle comes in, oh, I can show you. Wait. Let me show you like that. So the nozzle comes in and prints, prints your layers. And the thing is that the diameter, not the radius, the diameter of the nozzle is 0.4 millimeters, but that is just in X and Y direction, meaning that this is how thick the line is going to be in X and Y direction. But the height of the line, it can be squished, right? So that means you can go lower than the nozzle diameter. Actually, what you can't do is you cannot go beyond 75 or 70% of the nozzle diameter in height, simply because the layers, this strand of plastic that is being laid is going to be too cylindrical. So it's not going to be squished, meaning it's not going, the layers won't have a lot of strength between them. So you'll be able to pull the model apart much more easily. Does that make sense? Okay. So it's the thickness of this line, and that's exactly why if you have a wall that is less than 0.4 millimeters, it's simply going to be ignored. That's because the thickness of a single strand of plastic is 0.4, so it will ignore everything that is lower than that. Moving on, back to here. So 70% of the nozzle diameter is the maximum layer height. And I think 0.4 times 0.7, 0.28 is something that you shouldn't go beyond, right? So the thickest, for instance, 0.3, it would still work, but it wouldn't be ideal, right? So usually the way I print these models is I either choose 0.16 for high detailed models. Wait. Record, there we go. So coming back here to quality, this is I'm hanging on this setting. It's because it's a very important setting, to understand. Usually I start off with 0.2. Okay. Usually I start with 0.2 millimeters in layer height, and then kind of move on from there, either going higher to 0.24 or lower to 0.16 if I see that I'll need thinner layers to be able to print out that kind of structure. For something like this, 0.2 is absolutely okay. I could even go for 0.24 and it wouldn't make a huge difference. Then there is one thing, one very important thing is that the structure right here that I have, see how it's not touching the build plate properly, and we can kind of simulate it on if we or look at it. If we go to the right hand side view, or the furthest to the right hand side of our view, there is this kind of vertical slider. If we slide it down after slicing the model, if we slide down that vertical slider, you will be able to see the first layer. And the first layer is just like, it's just barely touching. The model is just barely touching our build plate. And this is because the model is not flat on the bottom, right? So this is definitely not enough for the model to properly stick to the print bed. So what I always do is I first choose the layer height, and then I go and look at the first layer. And if the first layer is not something that has a lot of surface area, then I'll choose my model, choose to move it, right? So you select the model, you select move, and in Z, you specify, for instance, -1 millimeter, right? So the whole model gets moved into the print bed by -1 millimeter, right? So the way it works, when you move the model down by -1, the way it works is things that are going to be kind of that 1 millimeter of the model that is going to be sticking into the print bed is not going to be printed. Of course, it's not going to be sliced, and the Cura only starts generating slices from the part that is sticking, out of the bed, above the bed. So now if I look at the first layer, since we moved the model down, I can see that my first layer looks like this, which is much better, right? Still not, minimize that, still not ideal, but much better. So what I'm going to do is I'll just move this model by 1 more millimeter, so -2 millimeters in total, down, slice it again. Oh yeah, now this is like a large surface, well, not a large surface area, but good enough surface area for me to work with. I will explain what the perimeter line around the, what this perimeter line does in a bit, but yeah, it needs to be there. Don't worry about it for now. So then there is this kind of initial layer height setting. If you don't see it, then you hover your mouse over Quality tab, and you click the gear icon, which appears. You click it, and then you will find right below layer height, you will find initial layer height setting. If you tick mark it and hit close, then it's going to be, appearing here. Alternatively, you can, if you click that gear icon, you can just search. So you just type in initial layer, and then it's going to give you initial layer height. You tick mark that, and you have your initial layer. So what this does, it changes the thickness of the first layer independent from all other layers. So you can have the first layer being very thick and other layers being thinner, or vice versa, right? And why this is useful, it's because, for instance, let's say you're printing something at a very, very high quality, 0.12 millimeters, right? But you want to make sure that the first layer kind of sticks well to the print bed, so you have a lot of plastic going on in the first layer, and also that it kind of self-corrects a little bit better, but that's not that doesn't matter. So then you change initial layer height to be 0.2 or 0.24, not 4, 24, something like that, right? So this is just additional functionality where you can change the thickness of the first layer that is going to be printed. And that first layer should never be like smaller than 0.16 and never be higher than 0.3 millimeters. Then I have line width here, but that doesn't matter. Now on to shell. So the shell is, okay, for me to explain what shell does, we need to change the way we preview the model. Right now, the color scheme is set to be by material color. If I click it and choose instead of material color, if I choose line type, it's going to give me different colors for different types of extrusion lines of plastic, right? So it's basically color coding what part of the model is it printing, right? So there's this kind of helper line, which is the blue one. And in this case, the helper line is just this perimeter here. Then we have the shell, which is red, and it's the outer perimeter line here, and the inner one. Then we have the infill, which you can't see right now, and you have top and bottom, which you can kind of see here, the top and bottom lines. So color coding itself is fine, but let's move that slider on the right-hand side to somewhere in the middle of our model, somewhere here. If I zoom into this, you can see 2 red lines and 2 green lines in a section, right? So those are our wall lines. And right now, our wall line count is set to be 2. Top layers is set to be 4, and bottom layers is set to be 4, meaning that it's going to do 2 lines on both sides of our shape. Wait, of our shape. Can I find a place where it? Yeah, this is a good one. Right? Yeah, there we go. So lost it. Wait, coming back. There we go. For instance, here, like in this part, there are 2 lines on the outside. Those are the shell lines, and 2 lines on the inside, right? The external perimeter, internal perimeter, internal perimeter, external perimeter. And then in between, you can see these kind of orange lines here. So those lines are what's called an infill. And if you slice a box, you don't need to do this part. This is just for me to show to you. Where is it? Where is it? Where is it? There we go. Box. Paste it here. So I have a box now. Slice. Okay. It's much easier to show it with a box. So back to here. Shell has 2 lines, right? Here. Set up here, and it has also it has infill. So this grid right here is the infill. So anything that happens when in between the shells is an infill, which you will be able to control by yourself. But basically for strength, if you need to increase the strength, it's not the infill that you're increasing, not the density of this grid that you're increasing, but rather the amount of how many perimeter lines it has. So shell thickness, right? So if I change wall line count to be, let's say 4, and hit slice, you can see that this is how, how thick the shell of this box is going to be. For beautiful, like for just nice looking models that don't need to be strong, you just use 2 shells, 2 wall lines for the shell. For something that you need to be somewhat strong, for instance, a box for electronics or something like that, you would use 3 lines. And for mechanical parts, you would use like 5 or 6 shells to make it really strong. When it comes down to top layers and bottom layers, you don't need to mess with those. Just to explain what they do, let's talk about top layers. So, So this is the first top layer that it makes, right? Just fills it in. Then second top layer, third top layer, fourth top layer, right? So it just makes 4 top layers, and it does the same thing for the bottom. So this is how solid the top and the bottom is. Kind of easier to see on a box rather than on this this form right here, but it's exactly like it's doing exactly the same thing for our form as well. All right. So shell-wise, you don't really need to mess around with it at this stage. Just keep in mind, if you need a stronger print, you just do 3 walls rather than 2. Infill. So back to here, this is infill density set to be 20%, with infill pattern set to be a grid. Infill density-wise, for something that just needs to be pretty, you can get away with something like 10% or 12%. I'll just choose 12%. This is just if you need it to just be pretty, right? You can get away with this kind of density for the infill. And when it comes down to infill pattern, it's absolutely up to you. Personally, I like using gyroid infill pattern. It's basically this kind of form. Just simply because as the 3D printer is printing it, and can I show it? Play. Where is it? Come on, do that. Yeah, there we go. As 3D printer is printing it, it makes a nice sound. that's about it. That's why I like this pattern. It just goes like woo, woo, woo. It's nice. Anyway, you can choose any kind of infill pattern you want. If you need your parts to be extra strong, then you can choose infill density to be like 30% or something like that. But anything higher than like 40% has extremely diminishing returns. So it doesn't make sense to do anything higher than this. Okay, I'll choose 12% here. Material. Okay, so this is an important part here. There are different kinds of materials with which you can print. The most common ones are PLA, filament, and this is the filament that is used in the school, right? So PLA filament. Let me try and, doesn't matter. So PLA filament is, first of all, it's made out of corn, which is cool. It's not biodegradable, but there is another word. Biodegradable means that it rots. It doesn't rot, but if you leave it, if you dig a hole in the ground and you place your PLA prints, 3D prints in the ground and kind of bury it, then I believe it's 2 or 3 months until it completely gets broken down. So it's not biodegradable, but there is another word for it. I don't remember that English word. PLA plastics print at the lowest temperature of all of the plastics. So usually when printing with PLA plastics, you just check the spool where the plastic is held, and it will tell you the required temperatures. But the really good rule of thumb is your printing temperature should be around 200 or in between 200 and 205 degrees, something like that. So I'll just change the print temperature to be, in this case, 205 degrees. Why not? And then what I really like to do is basically when you're setting up the print, you are fighting you're fighting for the print not to peel off from the print bed. That's the main thing that can go wrong, is that as it's printing, you know, halfway through, the print will pop off from the print bed and it's just going to do a noodle fiesta on your print bed. So you need to make sure that this first layer sticks properly, right? And that's why I always have separate controls for the first layer. For it to stick properly, what you want is you want more plastic, right? So that's why, or enough amount of plastic. That's why initial layer height, I always lock it to 0.2 millimeters, even if I'm printing everything else, especially if I'm printing everything else at 0.12 millimeters. Second of all, you want to always print your first layer hotter, right? So it needs to come in hot. And you always want to print your first layer slower. So first of all, printing temperature initial layer. If you don't have the setting, click the gearbox and type in printing temperature initial layer. There is initial printing temperature. No, it's not the one that you want. It's printing temperature initial layer. Choose that. Choose that, and then you will be able to change the temperature of the first layer. And also the rule of thumb is 10 degrees more. So if you're printing something at 205 degrees, then the first layer is going to come in at 215 degrees. If you're printing something at 200 degrees, the initial layer is going to come in at 210 degrees. The colder the printing temperature, and PLA plastic printing temperatures not vary between, but PLA plastic can be printed somewhere between 190 degrees up until 220 degrees. If it's colder, let's say if you're trying to print it at 180 degrees, then the plastic will not melt properly and it's going to make this kind of a ugly clicking sound. And it's not going to print properly. If you're printing at 230 degrees, the plastic, PLA plastic will degrade and it's going to make an ugly, like it's not going to be nice, and also it's not going to smell nice. It's going to start kind of burning just a little bit, but nothing to be concerned about. It's just, you know, not nice. There is something else about the plastic. Yeah, for this tutorial, not tutorial, but for this workshop, we will be using the plastic that the course will provide. But once this workshop has been finished, then you will need to get your own spools of plastic. You can get those from Jonas' office on the 5th floor. I think it's on Tuesdays and Thursdays. One spool of plastic of PLA plastic costs 300 crowns, and it's 1 kilogram of plastic, right? For instance, printing out these two shapes here, you know, the full-on box together, or I can just delete the box for a bit. printing out the shape will require 13 grams of plastic. So if I calculate it, we can print out 77 of these models with a single spool, which is a lot. Which means that you should share spools. There's no reason not to, right? During the course, I think 3 people per spool would be absolutely fine, and that comes down to 100 crowns per person for the whole semester. I think that's a good deal. Yeah, Jonas is around in the school. How many models will you have? Well, honestly, it's up to you, but I would suggest printing, like just choosing to print 1 model per week until the final review. Yeah, something like that. This will force you to kind of work. I know that, you know, with this distance learning, it's kind of hard to force yourselves to work. But if you just choose that I am going to make a single, you know, a 1 3D printed model per week, then it kind of forces you to you know, make decisions basically, and keep going forward with the design. And it's actually it's about everything. This is a little bit different of a tutorial, but to learn anything, you need to kind of tell yourself, give yourself some sort of a time frame, some sort of a schedule. For instance, that character model that I've shown, I have just started learning Blender starting this year. And I have just told myself that I will be doing 1 model per day of something until I can make a character, right? And I think it was 24 days or something like that. So 24 models in 24 days, and then eventually I could actually produce a decent model. So keep that in mind, right? It's there are no shortcuts. It's just practicing. Same thing with rendering. Like I've started this year. Let me show you. Like I've started this year by just learning how to render, and how to render different things with different styles, just because I wanted to first of all prepare for the rendering course that we had, but also to kind of see, you know, what's out there. So I would do a 3D model each day, and then I would render out that 3D model in some sort of a with some sort of a new method that I didn't know so far, right? So in this case, these are cell shaded models, and I've showed them during the rendering course. In this case, I was looking into how I can work with 3D scanned models, perhaps. Composition, learning basics of lighting and composition. This is where I started to learn sculpting, 3D sculpting. So this was done during day 1. That's day 2, model from day 2 of sculpting. That's those are the models from day 3, day 4, day 5. Yeah, you saw this 3D printed. I just wanted to see. Let me go back here. I just wanted to see if these incisions are going to print out properly. Because anything that I do is always related to different courses, and we will be looking at how to use these techniques in this course as well. Not rendering techniques, modeling techniques. That's day 5. That's like, I think I skipped 2 days and I worked on a different computer. So this is like day 9 or day 10, something like that. Just modeling out this helmet here. That was like day 12. So I came back to cell shading to actually look at if it can be recreated in a different manner. Right. So that, and this is I think day 20 or something like that. So half of the stuff that I have is on the other computer. Doesn't matter, but whatever. The main thing is you need to schedule. You need to create a strict schedule if you want to get good, right? And you need to follow that schedule. Or else it's just, and everything that you do needs to be analytical, meaning that if you just repeat the same thing over and over that you know how to do, you will never get good at it. You will never get good at other things. You will get good at that particular task, but if there's a curveball, if your client needs something slightly different, then it all will break down, right? And you won't be able to produce anything. So with every step, you need to kind of push yourselves and try to get out of the comfort zone and try different tools, different methods, and different approaches. And not just try, but actually solve problems with them. If one tool cannot solve your problem, then maybe another one will be able to. Rule of thumb is if it cannot be solved with Grasshopper, then you just run freaking Rhino and model it out by hand in, I don't know, 10 hours or so. You just sit down, run some sort of a synthwave mix and just go to town at it. No shortcuts. Coming back to here, to this model. There's also an option for the build plate temperature. So for PLA, it's always 60 degrees, always, right? So you just keep it at 60 degrees. For other materials, which are a little bit more advanced, and you will not be using them during this course, it can go as high as 120 degrees, which means that if it's printing with a build plate at 120 degrees, you should never touch the build plate then. But in the school, we try to not use those kind of materials. First of all, because they're it's not like they're toxic, but they have a smell, right? And that smell is kind of, your head will start hurting if you're in the same room as the 3D printer and it's printing in those kind of materials. The melted plastic smell, it's not nice. PLA, on the other hand, doesn't have a smell. Well, unless at the start of the print, it kind of has a little bit of smell, but later on, it doesn't have any smell, which is much nicer to work with. Okay, so that's material. Now we have speed. Print speed is, okay, so print speed wise, you always use 60 millimeters per second. So the nozzle, as it's printing, is going to be moving at 60 millimeters per second, except the outer perimeters, so the red lines, are going to be done at half that speed. So they're going to be done at 30 millimeters per second. And also the first layer, right? I always change the print speed for the first layer because I want it to be coming in slow and hot. So if you don't see initial layer speed, you should click the gearbox next to speed and choose or type in initial layer speed. Tick mark that. And instead of 30, use 25. So even lower than the suggested value. 25. All right. So that's, actually, we don't need to change anything else about this. 60 and 25 is very, very generic, but it works for like 99.9% of the 3D prints. Then we have travel. So travel-wise, do you all see in the travel, do you all see enable retraction, retraction distance, retraction speed, and Z-hop when retracted? These 4 options? Do you see anything in travel? Which ones do you see? The retraction ones? Just enable retraction and Z-hop. Okay, so both of them need to be turned on. Enable retraction, turned on, Z-hop, turned on. When you turn on the Z-hop, it will ask you for what's the Z-hop height. And that should be, no? Oh, it doesn't give you Z-hop height. Okay, if it doesn't give you Z-hop height, you just click the gear, type in Z-hop, and find Z-hop height, tick mark that, and now you have it. So how do I explain it without, I know. We always use the whiteboard for this. New, yeah. There we go. So let's say you have a shape that is something like this in the section or in a facade, doesn't matter, right? And it's going to be printing it, layer by layer. So it's just printing it. That's cool. Until it reaches this, and it's kind of going to continue printing it until it reaches this part where it needs to print this part and then this part, then jump back to this one, then jump back to here, and kind of keep jumping between these 2 legs, right? So it's printing this layer here, and then it will continue on printing this part, but there's a break, there's a jump, right? So what Z-hop does, as the nozzle is printing, and then it finishes one island of that particular layer, for it to jump to another island, what it's going to do, it's going to lift the nozzle up, go to the new position, and start and kind of pull it down again and continue printing this layer, right? So there's going to be this kind of book travel. Some of the options are checked in the expanded menu, but don't show up on the right when I close expanded menu. For instance, okay. For instance, Z-hop height, if I have Z-hop when retracted turned off, right? If I have this turned off, then Z-hop height is hidden from me. If I have this turned on, Z-hop height is shown, right? So it, even if those settings are tick marked, it doesn't mean that they will show up. It will just show you the stuff that you can change, basically. But what are the options? Yes, we will have a break after this. What are the options that are hidden from you? Oh, less than a minute left. Oh, that's fine. Those are fine. Okay, let's have a quick break, 15 minutes, and then I will call you back. And the fact that those are options are hidden is fine. Absolutely. Okay. Where were we? Retraction distance and retraction speed not showing up even though they are enabled or ticked. That is absolutely fine. Those are the two settings that you need to, you don't need to worry about those two settings. Yes, and also the Z-hop though, I will go through it now, but just for the retraction distance and retraction speed, it's as the nozzle is just traveling, as it's not printing, but it's traveling from one part to the other of the 3D print. For instance, let's see, somewhere here, right? So it's printing the first part, doing da, 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 and it kind of travels to the second part of the print. So what retraction does, it pushes back 0.8 millimeters of plastic into the nozzle, or not into the nozzle, but away from the nozzle, so that it's not printing. Veronica and Albert. Invite. Where is Albert? Can't find. Wait, Albert's here in the Zoom meeting. Okay. Cura, there we go. So as it's traveling from one part of the print to the other, it's going to push back a little bit of plastic so that it's not extruding, so that you don't get a lot of these kind of strings between the two places where it's printing. So it's basically so that the printer doesn't seep plastic as it's just making travel moves rather than printing moves. Z-hop is, I've showed it with this awesome diagram here. Once it stops printing one part, finishes printing one part, it's going to lift the nozzle and kind of pull it down again once it starts printing the second part. And it's going to kind of always lift the nozzle during these travel moves between the two pieces in a section, in a single layer. The reason why we use Z-hop is so that if the plastic is curling up, or if something is happening where the plastic is kind of higher than it should be, the nozzle will not hit the plastic, right? And it will not hit the whole print away from the print bed. Z-hop height, 1 millimeter is actually fine to use, but usually I like to do it even lower, 0.6 millimeters. You don't need to move it high for this to work. Mia just gave us a link to something. I will not be clicking that. So that's Z-hop. On to cooling. So as the printer is laying out molten plastic, Once the plastic is laid down, it needs to be cooled as fast as possible. So there's a separate fan that the 3D printer has, which cools down the plastic as it's being laid down. And I think all of you will have, if you have enable print cooling turned on, and you should always have it turned on, I think all of you will have those two settings, fan speed and regular fan speed at layer 2. No? Well, if you don't have them, then just not the sub. Oh, the regular fan speed at level 2. Okay. Click the gear. Fan speed, regular fan speed at layer. Tick mark that. Once you have that ticked, you'll be able to choose at which layer does the printer start cooling the plastic. So remember when I said that the first layer needs to be hot and slow? That's precisely why regular fan speed at layer 2 is set rather than layer 1, meaning that the first layer will not have a fan that's blowing on it and cooling it down. And then immediately as you start printing at layer 2, it's going to start cooling down the layer 2 part of your print. So all of these settings, 100% is, oh yeah, you always keep it at 100%, and the fan should kick in at level layer 2. So cooling is an important thing. And the reason why it's important is, I can show you, print cooling PLA with and without. Am I? Yes, I am. That images. Oh, this is a good example. So this frog right here, this is without print cooling, and this is with print cooling, right? So you can see the change in quality. And where do we have it? And yeah, for instance, these two guys, the left one is with print cooling and the right one is without. So you can see that it's much more mushy if there is no cooling involved, right? The plastic cannot cool itself fast enough, and then as you keep building it up more and more, the plastic will, not keep its shape properly, and it's going to make all sorts of mistakes. So print cooling is an important thing, and it should always be turned on. In some cases, such as with some materials, such as ABS, plastic, too much print cooling. Yes, I guess this one is fine. If you have with other plastics, so this is ABS plastic, same one that is used for Lego bricks. If you have too much cooling for ABS, then it's going to warp like this, but PLA doesn't suffer from that problem. So there's no reason why you shouldn't use full-on print cooling. Support. Okay, so this is where it gets interesting. Right now, if I look at it, at how this shape is going to be printed out, somewhere here, right? So it's doing its thing, it's printing the shape, and now it needs to go up one level, like that, like that, like that. So it keeps going up. And you can see that basically like this layer right here is just going to be, all of these lines are just going to be printed on air, right? Straight up on air, which means they will sag and it's not going to look that nice. It still can kind of do it, you know, it's doable, but the quality of the surface is going to be something that we've seen, where was it? Something that we've seen here on the left-hand side, right? It's going to be a pretty poor quality of surface. So this is where the supports come in. If I tick mark generate supports, and I assume you have, once you tick mark it, you have support placement and support overhang angle. Like you have three options here. At least you should have these three options. Other two, enable support brim and minimal support area. That's whatever, you don't need to worry about those, just these three. Do you have those? Super. So if I tick mark generate support and hit slice, kind of move the slider a little bit, you can see that this structure of supports was created. And that structure is going to hold my model in place, right? It's going to hold the overhangs in place. By default, it's set to be 50 degrees. So everything that is leaning out more than 50 degrees is going to be supported, which is a little bit, not a little bit, which is way too safe. For instance, if we have support overhang angle set to be 10 degrees and hit slice, it's going to support literally everything, right? Everything that it can support, it's going to support, because it's going to treat everything that is even slightly, you know, like 11 degrees off from being vertical. It's going to treat it as something that is not 3D printable without a support. So rule of thumb is I always use 60, in between 60 and 65 degrees. So I'll just choose 65 degrees here and hit slice. And then you can see that the supports are only placed here and they're pretty small compared to what we had with 50 degrees. So it's a pretty small area. If I feel lucky, I can choose 75 degrees, which is really, you know, it is a complete, it shows a complete trust in the 3D printer, the 3D printer's ability to do supports, and not to do supports, but in 3D printer's ability to do cantilevers. But with 75 degrees, there is, I don't know, like from my experience, you get like 20% chance of failure, right? Of it not just being able to do anything. So 65 degrees is still, you know, within the safe zone, and that's the value that I usually use for all of my 3D prints. Some people might say that 65 degrees is way too brave, and you should use 50, but don't listen to those people. They have no idea what they're saying. 65 is absolutely okay. So cutting it afterwards. The thing about the supports is that, is there a way for me to show it to you in a proper way? Let me. In between the support layers and the print layers, there's always a gap. There's always going to be a gap that I believe it's by default set to be the height or the thickness of 2 layers, right? So there's always a gap. So for instance, with these supports, what I would, how I would remove them is with my fingers. I would just take the supports and peel them out from the bed, not from the bed, from the print. In some cases, it becomes a little bit more tricky. Do I have examples here that I can show you? No, I don't. Whatever. So in some cases, they become a little bit tricky to remove. So then you use pliers. Probably should show you what pliers are, right? Pliers. These guys. Something like this. Those are, I believe, in class Olson, you can get them for 25 crowns or 15 crowns, something like that. These kind of pliers are, no, I mean, it's a little bit of a rough, rough tool, but these kind of sharp-ended pliers are really, really good. Cooling, do you mean once the print is finished, do I leave it to cool and then remove the supports, or what do you mean? So once the print is finished, it's already cool. So you can immediately remove the print or touch the print. You can even touch the print as it's being printed. That's fine. Don't poke at it because you'll probably make it come loose from the print bed, but you can kind of touch it. It's fine. For instance, when a little bit of plastic drips from the extruder, usually I just use my fingers to remove it. You shouldn't. Don't use your fingers. Use pliers. But technically you can, and it's not a big deal. I mean, it's 200 degrees of, it's heated up. The maximum amount of how much it's heated up, it's 200 degrees, meaning that by the time when, like in first like 3 or 4 seconds, it cools down to something like 60, 50 degrees immediately, right? So you can touch it, but yeah, just to be safe, use pliers even when, touching plastic. So you can remove the supports immediately. And that's it, right? So those are the three values to change here. And then we'll brim support, minimum support area, absolutely don't need those two. So at least at this stage. Then we have build plate adhesion. So build plate adhesion deals with the first layer only, and it helps the model stick better to the build plate. So there are 4 types of build plate adhesion. There's skirt, brim, raft, and none. None is, well, none is none. Nothing is going to be happening, right? Skirt is this guy right here. This is a perimeter, right? So skirt is used when you have a lot of surface area. For instance, you're printing a box, right? And you have a lot of surface area and you don't need additional help from the printer to increase the surface area. So you just do a skirt around it. What skirt does, all that it does, it just makes sure that the plastic is flowing, right? So it will do like 2 or 1 perimeter around your model to just make sure that the plastic is going and it's going to start printing. And the skirt you'll see here is also always the first thing that's printed, right? So right now the printer is doing its thing and making sure that the plastic is flowing. And once it's done with the skirt, then it will immediately jump and, oh, it wants to do a second. Okay, sure. It's going to do the second line, and then it will immediately jump to the print and start printing the first layer of the print. So this is just to make sure that everything is A-OK. Oh, and it actually starts from printing the supports. Yeah, that's fine. Okay. Let's do that. So that's skirt. If I change this to brim, hit slice, and look at the first layer, this is how it's going to look like, right? So it's going to make these kind of offsets from my model and also from where the supports would be. And it's going to make this kind of a, well, it's a brim. It's called a brim. So it's going to make this kind of a brim. So what brim does, it increases the surface area for your model to grab onto the build plate. Usually, for instance, if I were to be printing this shape out, I would be using a brim, just simply because this surface area of the model itself that is touching the build plate is way too low for my taste. I prefer to have much more surface area. And also, every time when I'm using supports, I always use brim just to make sure that the supports are also have, that the supports are locked in place and they won't fall off or anything like that. So brim is definitely your friend. Then you have raft. So raft is an overkill, and raft is usually I use raft as a last resort. It's when I will start printing, like the raft is made in separate layers, right? So it's going to start printing something like this, right? And then if I look at layer 2, it's going to do another layer on top of it, which is this. Then layer 3, more plastic. Layer 4, even more plastic. Layer 5, supports are placed. Layer 6, the first layer of your element is placed, right? So notice how the raft stopped at layer 4, and then during layer 5, it's basically like leaving a gap, a small gap. And then layer 6, it only starts printing the model at layer 6. It means that between the model and the raft, there is one layer gap, which helps you remove the raft from the model. So raft is used when nothing else works. And honestly, in my 4 years of printing experience, I've used raft like 2 times maybe. So this is a complete overkill. Usually, like brim, I use brim 80% of the time. I use skirt 20% of the time, and I use raft 0.0001% of the time. And then you have a dual extrusion, which is whatever, and you have special modes, which is also whatever. You don't worry about those two. So these are all of the settings that you should worry about. Once you have everything calibrated, you are able to see what kind of print you'll have. And here in the bottom, you'll see it's going to take 1 hour, 34 minutes to do. And Cura's time estimate is usually, do you have subsettings on the brim? Yes, I do, but you don't need to worry about those. The default settings are perfectly fine. So the Cura's estimate over how long it's going to take is kind of good, especially when you're working with these kind of already calibrated setups where, we have set it up so that it's a Prusa i3 Mark III or Mark II printer. So that works. Wait. And then we have, so usually if I see 1 hour, 30 minutes, I know that it's going to finish the print in somewhere in between 1 hour, 20 minutes and 1 hour, 40 minutes, something like that. Then we have how many grams of plastic it's going to take, so 18 grams, and how long of a plastic strand it's going to make, so that's a 6 meter. That one doesn't matter. Usually I just check out the grams, but in your case you shouldn't check out the grams, because the only reason why I do that is so that I know, so that when I print a lot of elements, I know how many spools of plastic I will need, right? And then, so now you have your sliced 3D model, and you will choose to save to file, or if you have an SD card already inserted into your computer, then instead of save to file, you will have save to removable drive button here. If you don't have an SD card inserted, then it's just save to file. If your computer doesn't have a SD card reader, then you can use, in the 3D print lab, on the table right next to the printers, there's an adapter, a converter, SD to USB, right? So then you can just use that adapter. Once you're finished using it, please bring it back to the 3D print lab. That's the only one that we have, and that one doesn't belong to our course. It belongs to the school, and they will have my head if some of the students just steal the adapter. So now I don't have an SD card inserted, so I'll just choose save to file. And I'll just choose desktop, and you can name it any way you want. I'll just keep it as default, hit save. And now this kind of .g-code file was created on my desktop, which is exactly the file type that is going to be used by the 3D printer. So this guy right here. I can actually show you, if I right click it, I can actually show you what's inside of that G-code file. And this is to explain, for me to explain better how 3D printer thinks and how it works. So the first thing that you will notice as I have opened up the G-code file with a text editor is that it's not compressed. Like this STL file, for instance, is compressed, meaning that if I open it, I have no idea, what's going on here. So the 3D model is compressed, but the G-code file is not compressed. And that's because the processor on the 3D printers and also CNC machines, the processors there are very slow compared to the computer processors, so they cannot uncompress and print at the same time. So that's the first thing. Then just going through it line by line, I can see that the G-code flavor is set to be Marlin. Don't worry about that part. Time, this is in seconds. So basically it tells the printer, the file itself tells the printer how long it's going to take to print, how much plastic it's going to use, is telling the printer what layer height it should use. It's telling the printer the location of the print, just telling it what kind of software was used to generate this G-code. And then it starts right at M82, it starts giving orders to the printer. So the way printer works, it just reads line by line of all of this, right? So M.82 is, well, it doesn't matter. It kind of explains what it says here in the comments, commented section, right? But it's basically until here, M104 command, S210, it is going to set this is a command that makes the printer heat up, and also this one. So this one makes the hot end heat up, and this one makes the print bed heat up. And then it just asks it to wait until it heats up. Once it finishes waiting, then it will start, going through all of these other lines. So for instance, G1, and most of the lines that you will see G1 are going to be G1, is movement. G1 command is move, right? And the way printer reads it is move to these coordinates, X position, Y position, and as you're moving, please extrude 2.4 millimeters of plastic. Once you've done that, then move to this position and extrude 2 more millimeters, 2.4 more millimeters of plastic, and then move to this, and so on, right? So it keeps going, right? Keeps going. So the 3D printer itself has no idea what it's printing, right? What kind of form it's printing or whatnot. All that it knows is, all that it does, it just reads every single instruction line from the G code, right? And kind of, does the print at the same time. Is this why we need meshes to 3D print? No, not necessarily. The reason why we need meshes to 3D print is simply because there is no slicer that uses that doesn't use STL format, and STL format is, the most basic mesh-based format. So that's the reason why. Okay, and once it finishes printing, then it's going to just say, turn off, stop heating the bed, turn off the fan, go back to your homing positions, disable all the motors, and then I don't remember, S0 is, oh yeah, this is like another one. So you can see here, make sure that it's not, turn off the heating. And then once it's done everything, there's an additional safety where it says, make sure that it's not heating, right? So it's kind of double checking that the printer is not heating anymore. And that is it. So you'll be able to see, so once you have your G-code here, G-code file, you'll need to load it into an SD card, again, either through an adapter or through or through directly by plugging in the SD card into your laptops. The school's computers don't have an SD card reader, unfortunately, so you will need to use an adapter on the school's computers. But I tested it and it works perfectly, so why not? There's one more thing that I want to show you, and once I've shown you that one, then we'll have questions and answers. Hello. So this is our 3D print lab, and I'm just going to quickly go through all of these machines that we have here and kind of explain what you can use them for. So this is a laser cutter. To be able to use it, you'll need to ask Jonas about it, and Jonas is going to give you access to basically log in to that computer and put your stuff in and laser cut it out. We will not be using that for now. Later on we will. We have 2 or 3 WASP printers here. So these are a different style of printer. These 3 printers, you shouldn't be using those. The big one though, you can use it, but if you want to, let me know. That one will need a separate tutorial from me for you to be able to use that. If we look here, we have our 5 workhorses. So these are Prusa style printers, and all of these are free to use. There are differences between them. These 2 are just default Prusa printers, and all of the settings that you've seen or you will see, all of the Cura settings apply to these two, and you can use them freely. Then we have this one, which has a multi-material extruder, meaning you can extrude with more than one material. I think it's it's 5 here. So this printer, if you want to use it, let me know, and we will arrange something. But I suggest not printing in multiple materials at this stage of your education. Then we have this one. This is very similar to those two in the corner. The only difference between this one is that this is running a larger nozzle, meaning it can push out more material, more plastic at the same amount of time. But this requires you to have to set it up properly in Cura. And in the tutorial, which I have already shown you, or I will be showing you, I don't know the time frame of all of this, you will know how to set up files for this one. And it also has the sign here that says that it's running a larger 0.6 millimeter nozzle, right here. Okay, then this one is an old one from China, and this one is for the Samtit course. The thing is that those print nicer, so might as well use those. But if all of those are being used, then you can indeed use this one for the Samtit course anytime you want. I will make sure that this one is kept open and unused by other courses for you guys. And then here we have there we have the clay 3D printer. That one, it's kind of disassembled right now. Don't ask me about the clay 3D printer. Used it once, didn't like it, doesn't matter. We'll be printing in plastic much easier. And that's that. So I'll just show you how to actually run it. Right, so first things first is you need to turn it on, right? And the on button is located on the side right here, right? So we turn it on, and it's going to make a sound, and kind of the screen will light up. So the next thing to check is whether or not you have material, right? So in this case, the material, the plastic is, was located on the spool holder. But the problem is that it got snapped. And usually this happens if it's raining outside and you leave the window open. The material will absorb moisture, and it's going to, over time, it's going to snap. So this is like worst case scenario. If you see this, if this happens, by the way, it doesn't snap while it's printing, it snaps when you leave it for a long time. If this happens, you need to first remove the strand of plastic that is here. And to do that, you click the knob, the circular thingy here. You click it, you'll get this menu, and you will choose to preheat it. Right? Preheat, and you'll preheat it to PLA temperatures. So I'm navigating through the menu by turning the knob, right, from one side to the other. So I will choose PLA, enter, and you can see that it's now preheating. It's basically, this is the current temperature of the hot end, which is, can you show it a little bit higher? Which is this guy right here. Basically there's this kind of nozzle thing. So that one's heating up. And the second temperature on the screen, this one is of the bed itself, right? So this one also is heating up to 60 degrees, right? So once it reaches around 190 degrees in the hot end, it will let me remove the plastic, this kind of strand, this strand of plastic that is sticking out, that got snapped. So let's just wait a second. Speaking about the bed itself, the plate of it is magnetic, meaning you can remove it, and it's very easy to clean and to remove your prints. It flexes a little bit, meaning if you flex it just a little bit, your prints should pop right off, and then you just put it in place, release it, and it just kind of sticks there, right? It's magnetic. The magnets are pretty strong, so watch your fingers, but that shouldn't be big of a problem. So now I can see that, you know, this is the current temperature and this is the desired one, right? So it's heated up now. So I can click the knob again, and I can scroll the knob until I see unload filament, right? If I click it, then it's going to poop out this plastic and make a beep, which means I can easily remove it, right? So now the whole hot end is without any plastic, meaning I need to put in some plastic. So with having the spool placed here, I will slightly unroll the spool. Oh, and can you show this? So you can see now there's a cross here, meaning that the spool got tangled a little bit. I want to make sure that that doesn't happen, so I'll just kind of push it back. There we go, and untangle it. And now this is, you know, it has a clean path. So to feed in the plastic, all I need to do is just not plug in, but take that plastic piece and put it in the extruder hole here, and basically you will be pushing it until you feel quite a bit of resistance. It's basically there are two gears here that are going to grind the plastic and feed it downwards, and those gears are not moving, right? So you're just cramming the plastic in between those two gears. Once I feel that, you know, that I can't push it any further, I will, in the menu, I will click the knob again, and I will choose load filament. And once I click it, it's going to start, come on, there we go. It's going to start catching the plastic and feeding it in, right? And it's going to take a little bit of time because it takes its time getting the plastic in. Oh yeah, and I don't need to hold it. It's just it's just my preference. So let's wait. Does it feed? And it's going to ask you, once it's done, it's going to beep and ask you, is filament extruding with correct color? And actually, I didn't see, like, can you show what's happening in underneath? Yeah, you can kind of see a little bit of plastic sticking out, right? So it's kind of extruding it a little bit here. Oh, by the way, don't touch that part is hot. But it's not, I want it to extrude a little bit more. So here I will just choose, is filament extruding with correct color? No. I'll click that, and it's going to kind of extrude a little bit more. And eventually I should see, yeah, there we go. So now you can see it's pooping out plastic, right? Which means that the whole hot side is filled with plastic, and we can start printing. Right, so now it's asking me that question again. Is the filament extruding in correct color? And then I will just choose yes. Which means, and now we're back to kind of square one, but now everything is set up with everything is ready for printing. So now what you do is, you can see here that it's still hot, right? 215 degrees and 60 degrees. So you will click right underneath the knob. There is this kind of a X sign button here. If I click on that, this is a hard reset. And that hard reset cools down the heat bed, it cools down the hot end, it cools down all of these parts. Which means that then I have plenty of time to take the SD card from the side, like that. And you can see that the SD card comes in not like that, but like that, right? It comes in upside down into the into here. So I take that SD card, I put it in my I take the SD card, I put it in my computer, I upload the G code into it. Can we do that? Yeah, let's do it. Ah crap, fingerprint sensor. Wait. There we go. So I just put it in my computer. And I'll choose a file that I want to print. So in this case, I want to print something like this. I'll choose all of the settings. So let me just double check. That is fine, that's fine, fine. That is fine. Yes, supports, yes please. Brim is A-OK, maybe more. Okay, I'll slice it. Oh, come on. Slicing. And I'll choose to save to removable drive. Or, alternatively, you can save to file, so it will just save the G-code file and you can directly import it into the SD card, you know, copy and paste it into the SD card. But Cura has a nice setting where I can just save to removable drive as long as it's plugged in. I click that. It's gonna save it. There we go. I'll eject it and I'll just take the SD card. So now with that SD card, we come back to the printer, we plug it in. So click the knob, choose print from SD, click that, choose the file name, usually it's right on the top of the list, click the knob again. And now it's going to heat up again, and once it's done, it's going to start printing. So there are a few things that you need to be mindful of as you're printing. The first one is if the first layer is not sticking properly to the heat bed, if it's peeling off or something's happening with the first layer that's not nice, then you need to stop the print. Remove the heat bed, remove the crap plastic from the heat bed, and make sure that that this plate here, this whole thing, is clean, right? So the best way to fix it is by using soap and water, right? So you just wash it off clean in the school's toilets. You wash it clean, you wait for it to dry, or you just use paper towels to dry it off, and then you try printing again, right? And then it usually always sticks, right? So it's the finger grease that messes up, right? So now it started printing. So the first thing that it's going to do, it's going to calibrate itself and find 9 height points on the print bed. Basically, that way it understands what should be considered to be zero height at different different places of the heat bed. Just a little bit of crap here. So it's measuring those 9 points. Once it's done doing that, it's going to make this one line here. It's going to draw a single line, and it's basically just for the printer to make sure that that the filament is flowing. Right after that, it immediately starts printing. Right? And it's hard to see whether or not the first layer is, properly sticking or not. But if you look at it from an angle, you'll be able to kind of see the plastic being deposited. Come on. Yeah, there you go. So you can kind of see it. And that's it. So basically you need to wait until the first layer or even the second layer has finished. And if there are absolutely no problems with the first or second layer, you're good to go. So you just leave the printer to do its work, and you come back and pick up your print in a matter of hours, right? And that concludes our tutorial. Honestly, these printers are built in a way that it's very easy to set up and it's very easy to use. If you see that something is really messing up, don't try fixing it, please. Let me know, I will fix it. I don't want to replace the whole damn printer, but usually that never happens.
Tell if the print is going wrong, what button to press.
Oh yeah, that's good. So if the print is going wrong, if you see that it's messing up, you click the knob here, you scroll until you see stop print, and you click it. And then once it stops the print, you just hit that reset button. Now I don't want to stop the print, but you just hit that reset button. So what it's going to do, the stop is going to make all movements stop, so the printer will stop moving, while that X button is going to make everything immediately start cooling down. So it's like two safety mechanisms. So again, it's clicking the knob, going down here, hitting the stop print, and then clicking the X button. And that's it. Now that's it, I think. Did I miss anything?
After you finish the print, turn off the printer with
Yeah.
the same button.
Yeah. Once
on
the
the
print
side.
is finished, you just click and the printer will turn off. That's it. Now that's it. Okay, happy printing. Record. So now we have our kangaroo definition, which kind of works on a flat piece of surface. And yesterday I've shown you that you can indeed, as long as you're working with patches, you can create a structure that is much more sophisticated than just simply a two-dimensional series of patches that are just being displaced upwards. To kind of reiterate, I can show you this method here. And you don't need to do this. This is just me reiterating what we've learned during last time, like yesterday's session. I'll just create a 3-point rectangle from here to here, and then up to here. And so I have one vertical rectangle here, and then I will create one more. 3-point from here to here and up to here. So I have two rectangles. Remember that this area right here is a hole, right? So this area is a hole. So that's why I can do this. If this was not a hole, that would mean that this edge is shared by 3 patches, which means it's a non-manifold edge, and this wouldn't work. So topology, and this is called topology. Topology is very, very important when dealing with these kind of, when just modeling any kind of structure, topology is extremely important. So I'll just reference these in, set multiple. Oh yeah, I forgot that this is how it, that it will find the freaking anchor points here. I keep forgetting that it does that. That's fine. We can look how it would act if these anchor points were also caught, and then I'll clean it up. So let me reset. Look at the preview. Oh lordy. Okay, that's not great. Okay, so the first thing to fix now is I don't want, if I have multiple layers of patches, I don't want these regions which describe where my anchors are to catch the points that are on all of the levels. I just want the ones that are in this inside of the region, but rather not on top of the region. To fix that, instead of using in-curves command here, where we describe the anchors, instead of using in-curves, I will ask in breps. Nope, that's not a command. Let's see how it actually, what's its actual name? Point in breps, sorry. Point in breps. Again, it's very important that it's plural, singular, plural. That is plural, breps, not a single brep, because we'll be using more than one. So point in breps. I do that, I select that. And now we have this node here. So it works in exactly the same way as point in curves, only that this one requires you, instead of curves, of course, it requires you to have closed volumes, closed breps. And it's quite easy for us to do it. If we just select our curves, these red regions, anchor region curves here, and we just use extrude curve command to extrude them upwards. Then we have options for choosing whether or not they should be solid, meaning should the top and the bottom of the extrusion have a surface created so that it's, it's an enclosed volume. And also we'll have an option to choose whether or not we would like to delete the inputs. So here I'll just choose it solid yes, delete inputs yes. Basically, once I create the volumes, I don't care about the curves anymore. And I'll just create, I don't know, some sort of a height for these boxes. I'll just, I won't type anything in. I'll just use my mouse to kind of create these boxes here, like so. Right? So now, all of the points that are inside of these boxes will be regarded as anchors. The problem is now that the boxes are laying right on top of the patches. So the points are neither inside or outside of the box. They are on the surface of each of our boxes here. So I will just select my boxes, that. I'll change their layer to be anchor regions layer, just so that I still have everything color coded, like that. And I will just move the boxes slightly down so that I make sure that the anchor points are going to be inside of each of these 3D regions. Then I just reference in the boxes by using brep container, boundary representation, brep container, right click, set multiple BREPs, select, 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 hit enter, we have them referenced. And basically to move, to carry on, here we have, if I choose to show you the Weaverbird vertices component, here we have all of the points of the flat mesh. Well, right now it's not flat anymore, but all of the points of the mesh before the simulation. And here we used in-curves component to extract the ones that are inside, that were inside of our red curve regions. Instead of using the curve component and in-curves component, instead of these two, I will delete them. We will be using a BREP and a point in BREPs component. So let's see what it asks us. It asks us for BREPs for inclusion test. That's good. I can just connect BREPs like that. Easy. And then it asks us for points for inclusion test. Okay, I can choose the points here and connect them like that. And then the last one is it a strict test or not a strict test? We don't care about that part. We will leave it as it is. Don't worry about it. And the output that we get is true or false, depending on whether or not the points are inside or outside. So it's checking for every single one of these points, and it's giving them a value of either yes or no. Is it inside or outside, right? So according to those values, here we were removing the points according to some sort of a yes or no statement. So all I need to do is I need to connect the inside output, the inside output to the pattern input of the cull, like that. Let me run the solver again. Why does it not work? But that's because I'm not previewing anything. There we go. So now it all works, and now you can see that this guy is doing some sort of a thing. Oh, and this is actually a very good example that I need to show you. If I bake this guy out now, and I look at it in Rhino, see how here the shading is messed up? And I went through all of those cleaning procedures in Grasshopper, right? So it's definitely not something that, that can be cleaned easily. It's something about the geometry. And this is where the topology comes back to haunt us. If I were to choose color back faces to be turned on, let me check the chat. The last step was, just to show you the last step, I connected the points in BREPs component to the cull pattern input. So I'm using the output from this one as my selection for which points are going to be regarded as anchors. Okay. So coming back here, I have colored the back faces, right? So the front face is gray, the back face is blue. And everything here seems to be very, fine and so on. And the problem happens here. And the problem happens not because we messed something up with the definition or anything like that. It's just simply we have accidentally created what's called a Mobius strip. If you don't know what a Mobius strip is, you should, but Mobius strip, let me just Google that for you. So a Mobius strip is something like this, right? A strip like that. It's basically a cylinder, a circle that bends 180 degrees, right? And reconnects onto itself. So this is what's called a single surface surface, no, not single phase surface, meaning that if you take a guy and the guy walks along the surface, after doing one perimeter along the surface, he's going to be on the opposite side of the surface. And then as he's doing another perimeter, he's going to be in the top again, right? So just with a straight line which goes along the surface, you can go to both sides of it. Seems cool, but absolutely horrible when you need to thicken this, right? Because now if I try to offset mesh, hit offset, you can see how this messes up. And it messes up because it will always offset towards the front, towards the front of the surface. And in this case, this polygon is being offsetted towards us, while this blue polygon is being offsetted away from us, right? So there's a breaking point there. You need to be very mindful of this happening, right? If this happens, the only way to solve it is by actually changing the model. There's no other way. So how do you solve it? Well, here I can see that if I offset on both sides, it will still make a mistake, but less of a mistake. Both sides, okay. It still makes a mistake. It's not that visible, but see this X? This X is where it changes direction from inside to outside, right? So it's still messing up. So solving it. Here you can see that this part is outside, right? Not outside, sorry. This part is the back face, and it's bending and connecting to the front face here, right? So this bridge connects a front face with a back face, meaning that it's impossible, you know, it's something that is impossible to do without creating this kind of a scene, without creating a Mobius strip. What would happen if I took, there's too many things going on. Let me hide a few of them. That and hide that. What would happen if I took this rectangle and I placed it here instead, right? And let me just drag its points a little bit, like that, right? So now that vertical rectangle is not placed on this edge, but rather on this edge. And now let me align everything like that and like that. Just something like this, right? And then I will just hit the reset button. Look at the preview. So it's doing something like this. Bake it out. Move it to the side. And here I have solved it, right? As you can see, because now the back face is bending here and connecting to the back face here. So I don't have a Mobius strip anymore. So it doesn't matter where you connect these kind of loops. And it's not a nice loop, but we can make it nicer. We still have 20 minutes, a little bit more than 20 minutes left. So let me make it nicer real fast. So I'll be working with this guy and I'll be just creating one patch, 2 patches, 3 patches. I'll be deleting the big one, show, and I will be connecting the center patch with this rectangle here and this rectangle here, like so. So one rectangle here. and one rectangle here. I'm still not showing you how to do vertical displacement for the foundations, because I think it's much more important to understand how far you can push these kind of structures and how much you can do with them. So I'll just select my patches now and set multiple curves. I'll set them up. Oh yeah, and reset and bake it. But because it all comes down to topology, right? So we end up with something like this. Right? Some weird stuff starting to happen. Flipping off sides. When did I do the flipping of sides? Mobius, you mean a Mobius strip, right? Making it from a Mobius strip. Okay. Actually, that's fine. Here we have 3 good examples of of how to clean it up and how to continue on working with it. So here I've made a bridge, right? And every surface has a back face and yeah, change. There we go. Every surface or polygon, doesn't matter, as long as it's infinitely thin, it has a front face and a back face, right? So if you have something like this, change. This is fine, right? But if you have something like this is not fine because it won't offset properly. So the reason why this kind of connection happens here, right, in this part, is because imagine trying to bridge, like all we're just doing is we're creating a bridge. Oh, I know how to do this, how to explain this better. Just a second. Explode. No, not explode. Yes, explode. Edge, surface, list item. That, like that. Join. Wait, why is this not? Oh, this is weird. Oh, it's because I did it wrong. There we go. And grab join, flatten. I'm going so deep into this because this is a very important notion. And mesh, okay, delete, unify mesh normals, flip. Okay, so this mesh and this mesh, like these two guys, are exactly the same thing, right? Topologically speaking, they're exactly the same. We have, these legs, which are looking at us, and we have this kind of a cross system, which is looking back. So it's as if this whole shape is turning backwards, right? And showing us the backside of it, right? The problem happens when we try to connect this portion right here. Can I delete mesh faces. So let's see, something like that, and mesh tools, create a mesh face like that. The problem happens when we try to do something like this, right? And that's because technically, yes, this bridge kind of starts off from the back face and continues on here. This not bridge, stripe, continues on here, 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 until here it meets a front face. And this is a seam where it cannot be solved, right? So if I were to join and try and say, unify mesh normals, it's not going to do anything, right? So it won't let me unify the mesh normals properly, right? If I were to, yeah, there's just no way to fix it. So you always need all of the patches to connect front face to front face, back face to back face, right? So Mobius strips in our case is a very bad thing. Regarding this mesh in itself, wait, let me delete this part here. Show. Okay, so we have a lot of examples here. So regarding this surface here, maybe it's better if we, instead of using curves, if we use surfaces, because it's easier, perhaps it's easier for you guys to see it. So what I'm going to do is I'll just create a new layer and I'll call it patch surfaces, whatever, right? And we will redo this script so that we can use surfaces here instead of curves. And that is really simple to do because all of these curves are treated as if they were surfaces already, right? Because we're using divide surface command, which means that all I need to do is just recreate from the curves that I have in Rhino, I just need to recreate surfaces, right? So all of the ones that are flat, I can just select all of my patches. So I just right click on my patch layer, choose select objects, and I can type in planar SRF, right? Which means that all of the surfaces that are flat are going to be generated for me, which tells me that the curves which are not flat, you know, they didn't generate the surfaces, which is fine. I can do it manually, right? So to do it manually, I'll just choose the surface from 3 or 4 corner points tool, choose the correct layer, and just draw on top of my curves. There's no shortcut for this part. Well, there is, but this is faster than the shortcut. So I'll just draw like that, like that, like that. Always be mindful of topology. If you want to know more about geometric topology, I would suggest looking into, let me just find that website. Was it here? No, it wasn't here. Ah, crap. Was it here? No, it wasn't here. Okay, I can't find it. But yeah, just Google it, look at the Wikipedia page, and it will become clear. Yeah. To change to make it color front face, back face, you need to go to where you have your layers tab. You should see a display tab as well. If you don't see the display tab, you can click on this gear icon, which gives you the options, and then you tick mark the display. Right? So once you tick mark the display, this display tab will pop up, and as long as you're in like a shaded view or rendered view, it doesn't matter. As long as you're not in the wireframe view, you'll be able to, if you scroll down, you'll be able to see object settings, and you'll be able to tick mark color back faces to be colored, right? And choose the color for them. So I prefer using blue, but you can choose, any color you want. Okay. So back here, we as like in architecture in general doesn't deal with topology that much, simply because we don't, traditional architecture deals with boxes, and those don't worry about topology. It's just, boxes. But once you start working with more advanced surfaces, then suddenly how all of these things connect starts becoming very important. So now I have all of my surfaces drawn, but I have no idea in which layers they are. So I'll just type in cell SRF, select surface, enter. So it gives me all of the surfaces here. I'll just right click on my patch surfaces layer and choose change object layer. So now I know that all of my surfaces are in that particular layer. And this is the moment where we can test out if this is going to work visually even before relaxation, because now I can choose, oh yeah, and just in case, let's hide the patches layer where our curves are, so that we only see the surfaces. So in this case, I can start testing it out, right? And seeing, can I make all of this connect in a proper way, right? So this is the front face, this is the front face, this is the back face. Okay, so I need to flip this. So I'll just type in flip, enter. And now my front face, front face, front face, all of these connect. And then I have a back face here, which I also select and type in flip, enter. So now all of these connect properly. If I look at it from a different angle, this connects as well. Even though it makes this kind of a 90-degree turn, it still connects properly. This doesn't though. So I'll need to flip this guy. So now all of this area connects nicely. And then it's going to be this, 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 and this. Flip. And this is the one more that I need to flip. No, it's not. I mean, I do need to flip this one so that everything here connects, but we still have this surface here, which is inside out, and I will just flip this one. And now you can see that, all of the back faces, even though they bend into this cross, they continue on, and all of the back faces never jump to becoming a front face. They always continue being a back face in every connection. And every front face is doing the same. It continues on connecting to other front faces of the surface. So that's fine. That's good. That means this whole thing works. And we already know that it works from this. But then I can right click on the patches, patch surfaces layer, right click, choose select objects to select all of my surfaces. I'll go back to Grasshopper and create surface node, empty surface container, and reference them in. Set multiple surfaces. like that. So now instead of curves, we will be using, we will be using surfaces. So all I need to do is disconnect the curves component, and instead of it, connect the surface component. That's all that it takes. Then I will just reset the simulation, look at the preview, and it's not working. But of course, why would it work? Okay, let me troubleshoot. That is fine. That is fine. Mesh from points is, ooh, that is not fine. Hmm. Hmm. All right. Wait, the teacher got stuck. Mm-hmm. That is absolutely okay. Or is it though? Yeah, that is okay. Why do you not work? Oops. Oh my God. Okay. Set one surface. Or set two surfaces. Huh. That is indeed a bug. Or not. Let's see. Untrim. Okay. Shit. So these are trimmed surfaces. Like the ones where when we create planar surface. Yeah, okay. When we create planar surface for the flat ones that are on the ground, it creates trimmed surfaces, which doesn't work in this case. That is fine. We will just be rebuilding these, just cleaning them up and making sure that they work properly. I don't need the curve. So let's do it this way. Disconnect the surface component from the surface divide. And let me select objects. Okay. Select surfaces. I forgot that it does that. Set multiple. Okay. So we have our all of our surfaces here in this surface component. I will explode, or not explode, deconstruct brep. I will use deconstruct brep on these surfaces so that I can get all of their edges. And I know for a fact that it's always going to be 4 edges, you know, for each of these rectangular surfaces, because they are rectangular surfaces. So I will be choosing to use edge surface tool, edge surface tool like this, which asks me to give it 4 separate edges to rebuild the surface, right? So to do that, I need to separate these edges in this list into separate outputs, you know, edge number 1, edge number 2, edge number 3, edge, or in this case, edge A, edge B, edge C, edge D. And to do that, I can use list item, connect my deconstruct brep edge output to the list item L input, like so, which automatically will always give me the first item on the list, right? So that's edge A. So I connect it to edge A. And then I will create if I zoom in, if I zoom into the list item component, I can see the plus sign on the bottom of the component. So I'll press it. And once I press it, you can see +1 appearing, which is the second item on the list. So that's my edge B. I press it again, third item on the list, edge C. Press it again, fourth item on the list, edge D. Record button. Okay. So what we've done here is we took the surfaces, which might be trimmed, might be untrimmed, we're not sure. But what we're sure of is that all of them have 4 corners and 4 edges, right? And we have deconstructed them into those 4 edges and extracted those 4 edges. So wait, first, before answering your question, I have what happened. The question is, what happens if you use an organic surface instead of a rectangular one? So before answering your question, this is just, I'm curious, is curvilinear or curved in Swedish the same word as organic or not? Because it's something that, like, is curved same thing as organic? Like the Swedish language use the same same word. Okay, some mixed answers here. I'm asking that because okay, got it. Okay, because I'm asking this because for 5 years now, 6 years now, almost, it's the same. We have the same discussion with the students about, you know, what can be considered an organic shape and what should be considered a curvilinear shape. That's not the point of this question. It's just something that I find very interesting. So to answer the question, what happens if you use an organic surface instead of a rectangular one? It's going to, I can show you. I assume organic, well, now I don't need to assume, I know that by organic surface, you mean, you know, something like that, right? A Lay's chip or Pringles chip is organic. If I take that chip and reference it in as a surface, oops, that's not a surface, SRF. If I reference it in as a surface, and I use divide surface on it, it's not going to create a grid, but rather it's going to create rows of points, which means that later on, when I'll use mesh from points, which asks me to give it a grid, it's going to make a very, very messy mesh, and I won't be able to use it. Also, if you're using a non-rectilinear surface for this approach, you know, for kangaroo, there's another problem. Show selected. There's another problem. How the heck do you join them, right? It needs to have a very, very clean connection from corner to corner. If these surfaces don't have, if these surfaces don't have corners to begin with, that means that joining them is going to be a pain in the ass. There's more questions that I have about it. For instance, why do you need curvilinear shapes? I mean, can you tell that this was a bunch of rectangles to start with. The starting condition is something that you want to be able to control. No. Oh, I guess that's the, the answer to that was rhetorical. The starting condition is something that you need, that you are doing to be able to, wait, I'm trying to phrase it. You want to have the starting condition as simple as possible. Like even something like this is already quite complex. If I were to add curved lines, like curved surfaces into this mix, I would spend the whole semester trying to figure out how the hell do I connect two Pringles chips. And by the end of it, I would have exactly the same surface as someone else would have done it with a single rectangle, right? So always choose a method which gives you the most control. It's all about control with these kind of structures. If you lose control and you just press the button and you have no idea what's going on, and maybe it's going to bake out, maybe it's not, then once you need to actually start thinking about space and volume and starting to treat it as a building, it's going to be hell. So it's much better when you're starting off to begin with something very simple, right? And this is by no means simple. This is already, too complex, but I needed something to show you the three-dimensionality of it. But just to start with something simple and build it off from there, right? It's not about how many curves does the building have. It's about how well can you control the shape of it and the space of it. Yeah, let's finish off with this one real quick, and then we'll just have like 5 more minutes for questions. So am I recording? Yes, I am. So surface, we get the surfaces which are either rectilinear or non-rectilinear. Sorry, which are definitely rectilinear, but which are trimmed or untrimmed, right? And we're not sure. So we are going to make sure by exploding those surfaces into components, and one of those components is the edges of the surfaces, and we know for a fact that there's always 4 edges. And then we're going to use list item to separate those 4 edges for each surface into edge 1, edge 2, edge 3, edge 4. And we're going to use those 4 edges to recreate a surface just from the edges, so without any trimming information whatsoever. So we are left with a list. Well, it's not a list right now, it's a data tree right now of definitely untrimmed surfaces, which will work really cleanly. One more thing before we connect them to the surface divide input is we need to make sure that all of them are in the same list rather in different lists. So I'll right click on the output of the edge surface and choose flatten. Right? And then I can connect the surface output into the surface divide input. Okay. Now let me hide a few things and run the simulation. There we go. So now it works. Exactly the same thing as we had before. Let me just smooth it out a little bit. And that's way too much. And decrease the strength of the vertex loads to something smaller. Maybe this goal can be, so edge lengths maybe can be 0.75 or something like that. Let me bake, patch surfaces, or sorry, default. I'll just look at the shape. Well, it's inside out. It's not necessarily inside out. It's just an inverted version. Like we had this before and now we have this. That's fine. I can just select it and type in flip. Right. So everything that was front facing is now back facing. Everything that was back facing is now front facing. So I end up with geometry such as this. Right. And then, by the way, if I offset mesh, not both sides, just solid. If I offset this one, it offsets properly. I mean, it does make quick bends, so that this area, these kind of quick bend areas are problematic. But besides that, I think it does a great job at offsetting. Same thing for this one as well. Even better job here. Okay, and now we have 5 more minutes for questions. So if you have any questions about this or anything in general, just shoot. You know, right then. I'm just doing. I'm just trying to do some sort of a balcony here. Then set multiple points.
Could I ask about the blah, 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 what was it called for Cocoon? The not voxel, the grid for Cocoon.
Cocoon grid.
The one that is 10 by 10 by 10 by 10 by 10.
Yes.
So could you have it that like, so that one is 5 by 5 by 5 and then the points are each, so it has to be something like dividable by 10 or? No.
It can be 3.2 by 3.2. You know, so for instance, here I can choose it to be 3.
Yeah.
Right. But then there are a few things that I need to change, right? So the grid has changed to 3 by 3, meaning that, well, my starting curves don't matter anymore. Also, here everything is fine. Yeah, so here, then I need this to be changed to 3 as well.
Yeah, but I was thinking if you still have the radius or if the grid spacing of 10, could the radius of the point charge be
less?
Yeah, 5, because then it would be 1 point every other possible place.
Not necessarily. No.
Okay.
No, because if you have it by as 5, and this one is let's turn it back up to 10, and let's see. Come on, do the thing. Yeah, you can kind of see. Yeah, now it disappeared. This guy produces a bunch of really small meshes, right? So all of these have a radius of 5, meaning that if a point charge is lower, if its radius is lower than the grid size, the points will never, it's not like every other point will meet. The points will never meet. Right?
Okay.
That's the main thing. So the smallest value that you can have here to make sure that the points are meeting properly is the same as the spacing that you're using of 10. Or if the spacing is 3, then you can use 3. It's not limitation, it's just, it's a logic of how this whole thing behaves, basically. So yeah, I've shown you this part yesterday, you know, creating a balcony, for instance, -20. Okay, so it's disconnected now, but where is it? 10? There we go. So creating a balcony and stuff like that is much easier to do by just adding some points to the collection. Then there is one more thing that you can do, and it's, let me just remove those 4 points for now, just so that they're not in the way. There is one more thing that you can do, and it's have an inverted logic to how all of this looks. And that one is, I think I will be showing that one not today. No, not today, because that one will require us to go deeper into this part, you know, the rule sets and so on, which will be horrible to to work with. So, or actually, will it? Let me try one thing. I'll just try one thing. If that doesn't work, then we will do this tomorrow. Reset. Okay, that works. So it is not going to be a hard thing to do. Every time when a generation of these cells is being calculated, you know, when the game is played, is that current generation of cells alive or dead? You know, every time when it's getting calculated and being looped, it gives you this matrix of answers from here, which is basically, if I were to check, which is basically a bunch of zeros and ones, right? Zeros saying that in that row of points, first 2 are dead, the third one is alive, next 4 are dead, eighth one is alive, and last 2 are dead, right? And so on. So it goes through the grid and it just basically attaches alive or dead to each point. If you use, and then it uses that kind of logic to remove points from the grid that we have here, have set up right at the start, and it kind of moves those points into the correct height. In this case, the final generation, which is right at the top. So that's all fine, but the thing is that if you want to invert this logic and to have this not as a volume, but rather as a cave system, right? So basically what you need to do is everything that is alive becomes dead and everything that was dead becomes alive. So you invert it. And the thing that does that is called gate not, right? If I were to check, this is the original list here. And if I were to check with the, and don't mind that it starts saying it in words, but if I were to check what gate not gives me is that everything that was dead, you know, or false, and was 0 becomes true, and everything that was 1 becomes false. Meaning that if instead of just the output of pick and choose, if instead of that, we use gate not and connect it to our culling right here, right before culling of the grid points, right here, it's going to treat it as a negative, right? So everything that was alive will become dead, everything that was dead will become alive. And then if I restart the simulation, you can see that now we are dealing with a cave system. So that, probably I should bake it out so that it's much easier for you to see what's going on. So I bake out this guy, 50, no, more. There we go. No, not rendered, shaded view. There we go. And let me now delete the not gate and just connect the regular pick and choose. Run it again. Like that. bake it, default, okay. And I'll move it by the same value, minus 150. And from that, can I change the layer of one of them? I will just change the layer so that they get colored in a nice way. Color red. Okay.
How come that your, or what have you done to make your display of the preview not show the lines of the mesh? So it's just polished.
Here,
yeah.
That's just display preview mesh.
Okay.
I just turned that off. Yeah. So now if we look at it in the Arctic, in the rendered view, yes, you can see that, well, with some exceptions, it is treating all of this as, this is the original and this is the cave system. So it is treating, when we use the gate not, it's treating it as a cave system, right? So that's how you invert the logic of it. Kinda. It has its limitations, especially in these kind of angular connections. But besides that, kind of works most of the time. So that's that. There is very important thing. What was the dash to call before we used gate not? Pick and choose. This guy right here. Panic moment. Oh no. can't turn it back. Okay. As I mentioned yesterday, this structure right here is a little bit too rectilinear, right? And we want to break it. And then the project that I've shown as an example, it's a very good architecture company. Projects, scroll, our skyscraper, scroll. You can see that the outline of the skyscraper is not perfectly rectangular, right? It's making these steps, and it's a little bit trapezoid. And this is not something that we have simulated, but something that we have added later on. And also, where is it? I'm just trying to find it. Yeah, sure. In this section as well. Notice how we have two completely empty spaces for the elevators. That is also not something that we have simulated, right, with the game of life, but something that we have added later on. So I'm going to show you how to carve into the structure and also how to remove stuff from the structure. To do that, first of all, we need to create some sort of a form. And let's do something simple. Let's just do a cylinder, right? Something like that. Yeah. Just a cylinder that kind of is a little bit smaller than the tower or whatever form you have, right? So that there are certain parts of the form, of the cylinder automata form, that are sticking out away from the cylinder. I'll just give you a minute to do that. Not a minute, like 10 seconds to do a cylinder. And the reason why I choose a cylinder, or, it doesn't matter. It can be a sphere, a cylinder, any shape that is closed, right, will work. It needs to be closed because we will be checking whether or not the points that are used to create this kind of cylinder automata tower are inside or outside of the shape. Just like we've done with Kangaroo for choosing.
So it works with a mesh as well?
Well, it's not. Let me help you out. Right now, we only care about this. We only care about the points. Because the mesh is created from the points, meaning
Yeah,
that
but can you use a mesh as the volume to check?
Yes, absolutely.
Okay, perfect.
Yes. You can use the mesh. For instance, that is how. Where were we? Let me find that example here. Here. There. Scroll. There we go. For instance, this is how this building is following the landscape. The landscape is removing the points that are crossing into it, right? All right. So here we have a bunch of points and we have a cylinder. So I'll reference the cylinder into my Grasshopper file by just referencing it as a brep. If you're not sure if it's a brep or a mesh or a surface and you know how you should reference it, you can always use a geometry node because that one can be, you know, a point, a line, a mesh, a surface, a polysurface, whatever, right? But as long as we know that this is a brep, we can just reference it in as a brep, set one, like that, hide in Rhino. So now we have it in Grasshopper. The thing is that we might want to use more than one brep at a certain time, you know, or not necessarily a brep, a mesh or something like that. So then I would use, I would first remove the points with the first brep and then kind of repeat the command, even though you can do it separately, but I'm blabbing. Okay, let me just show you and then we will we will move on. Showing is much easier than explaining it by words. So we have a bunch of points, we have a brep. We only want to keep the points that are inside of the brep, meaning I will ask points in brep. Well, close enough, point in brep. I will use that command, not command, but that tool here, point in brep. Like that, which asks me for, to give it a brep for inclusion test. So to give it a polysurface, I'll just connect it. And it asks for points. So I'll give it points. And the third one is, it says, would you like the checking to be strict or not? We don't care. We don't care about the third one. It's just basically plugging in the brep and plugging in the points.
What point container did you plug it into?
The one that's right before the data dam.
Okay,
the one that
I found it.
all of the recorded points, yeah. So the answer that we get from this tool is false and true statements, right? It's basically us asking a question, is the point inside of the cylinder? And it's going through every single point in this list and going, no, yes, no, yes, and then so on, right? So we can use that to remove the ones that are outside of our cylinder by using cull pattern, cull pattern, cull pattern, which asks us for two things. First one is list to cull, list of points to cull. So this is going to be my whole point cloud that I have here. And second one is going to be what's the culling pattern, right? Those true and false statements. So that's the output from my brep inclusion test. And now if I hide everything except the cull pattern node, so if I hide everything, you can see that only the points that were inside of the cylinder are left. And I can connect those. Right? And if I look at the mesh, now it's going to look like that, right? So maybe the top, yeah, there we go. So in the top, it's a little bit easier to see the cylindrical nature of that mesh. Okay, so we've managed to do that, and actually this is a pretty cool. Wait, let me mess around with it a little bit. Like that, that. Not bad. It's a pretty funny mesh. Anyway, so we can now we are able to use the cylinder. And let me change this to wireframe view. We're able to use the cylinder to remove everything that is outside of it, which means that we can kind of change the cylinder itself, right? For instance, the orientation of the cylinder, so on. And we can mess with the shape as much as we want, and kind of extract only the portion of the shape which we are interested in. Oh, that's a bad bad example. Maybe like that. There we go. So we can end up with something really funky, right? Whoop. Something like that. Okay, so that's the first thing. And also remember, not necessarily a cylinder, right? And any kind of a closed shape will work. So you can go ahead and, you know, really mess around with the lofts and so on. So you'll have, by doing this, I'm showing you how to have full control over the outer boundary of the shape, right? So now you have control over the points that you are adding, like through the points that you are adding to the collection. And you have control over describing the outer boundary of the shape. You know, what kind of form do you want to have? And I think this combination of these two is very, very important.
So did you just use a not gate here as well if you want to create an empty space inside of it?
Yes.
On the
yes.
point in BREP?
I can show it. Exactly. So for instance, let's say I want another, and this time I will use, I'll continue using cylinder, screw it. So I'll use another cylinder, I'll rotate it 90 degrees, and I'll make it intersect here, maybe a bit smaller, something like this. So let's say I want this cylinder, this guy right here, to make a hole through my shape, right? So to make a hole. To do that, I will, first of all, reference in the cylinder. Oh, and yeah, sure. I'll just reference in the cylinder, BREP, like that. Set one BREP. And I'll use exactly the same approach, right? Point in BREP command. So I'll connect my BREP here. But now the question is, what kind of points do we use, right? And the answer is we don't use the original points because, you know, we already have removed a little bit from the original. Instead, we use what we get from the first call, right? Because these are all of the remaining points, and we are going to remove even more from them. So I connect my cull output to my second BREP inclusion test. And now we get the, you know, the inside-outside answers again, and I can use cull pattern again. And I'm going to, you know, this is like first removal of points, the first cull, and this is going to be the second removal of points. So I connect cull to cull, right? And my BREP inclusion test is my pattern. And then I connect the second cull into my data dam, like so. So now what you see here is that first we removed the big chunk, right? And now we removed again from it. But this is not making a whole, rather it's just extracting what's inside of the second cylinder. So we need to make it into a whole. And the way we do that is we just say, no, everything that is inside should be removed and everything that is outside of this smaller circle should be kept. So I will be using not, gate, not. And I'll connect my BREP inclusion test to the input of gate not and connect the gate not output to my pattern input here. And now this circle, sorry, not circle, cylinder makes a circular hole through my shape. And this is how we made the elevator shafts in our, whatchamacallit, in our tower, right? We just had 4 circles, 4 cylinders. If instead of a BREP, well, let me just make some room here, like that. If instead of a BREP, you want to use, let me clean it up. You want to use a mesh, right? If there is a mesh, a closed mesh that you want to use, and you want to check, it's the same thing, right? You are still checking with inclusion, but in that case, instead of point in BREP command, you will be using point in mesh. Nope. Crap. Mesh analysis. Oh, sorry. Mesh inclusion. Test a point for mesh inclusion. So point in mesh. It will ask you for mesh, for point, and it's going. The last one is strict again, which we don't care about, right? So for meshes, it's mesh inclusion. For BREPs is BREP inclusion, right? So these, okay. So now you have 3 different methods on how to control this whole thing. By default, and let me bake it out. Just I want to check out how it looks like. Bake default, okay. Shade it. Kind of cool. Sorry, I kind of sometimes do this. I just start modeling and become quiet. So you can, with using these 3 different methods, you can have a lot of control over the shape, right? The pattern itself is something that you can describe or can create through where was it? Through the starting curves, right? So the starting condition of your game of life, and also through the rules. Then you can add to the pattern that was generated by just adding points to the list. And then you can use cull without the NOT gate to remove everything outside of a shape. And you can use cull with the NOT gate to remove everything inside of already modeled out shapes. So this enables you to have a crap ton of control over what kind of shape you will have and what kind of aesthetics that shape will have. The nice thing, and this is where I'm gonna start talking about architecture a little bit. The nice thing about this shape, these shapes, is that they are grid-based, right? Meaning that it's still, the step size of a grid on this shape is still 10 units, right? Just like we ran through simulations. Meaning that once you start doing interior wall systems, as long as you're within that 10 unit step, minus 10, well, 10. As long as you're within that 10 unit step within the grid, you'll be able to create facades. For instance, here, see how these two lines and these two stripes of the mesh align perfectly? You'll be able to create facades in a quite a controlled and easy manner, especially considering that clipping plane is your friend and you should always be using that. But we'll be looking into it a little bit later, into how to create interior spaces and facades for these kind of structures. But this should be, a lot of, it should give you a lot of flexibility, these three tools. Are there any questions from you that you have? Writing in chat is fine as well. Okay.
I think it's fine.
Okay. Aesthetics wise, it's something that has a very strong aesthetical presence, meaning that if you choose this method, this is a bad example, I guess, right now, because we are maybe rendered. Let me make it red so that it's nicer to look at. So aesthetically speaking, this approach drives its own, aesthetics, and this is something that you will need to follow. Well, not need to follow, but something that you won't be able to change later on. It's basically, you will just be able to do either something bony like this, or something blobby like this.
Maybe that has been like maybe my problem, that it feels like you don't really have control over, like you can control the shape, but you can't really control what expression it has. It's like there's a certain amount of different ways you can use it, and I suppose that's like a part of the whole program, that it is a set of rules, but it feels like it's hard to transform it into something entirely different. And
transforming it into something entirely, and that this is exactly what I wanted to get to with this talk about aesthetics. Exactly. If you just rely on the Grasshopper script and you bake it out and you look at it, right, then it is always going to have the same look, right? The same aesthetic, because it is driven by an algorithm. An algorithm doesn't care, right? That you want to have a different aesthetic or something like that. All it cares about is following the rules. So the way on how you start breaking this, record. All right. Minimize that. So cocoon part. With cocoon, it's very straightforward, right? You have a curve, you kind of, let's say, you have a curve, you kind of reference it in. Why does this, and you have a pipe, right? You have two curves, you reference those both in. You have a pipe that is fatter in the connection between the two curves. End of tutorial. I mean, there are a few things that we can mess around with, though. And the first one is, by the way, I'm using the same file from the last Cocoon tutorial that we've done, only that I have removed some parts. So everything that I'm left with is curve charge, Cocoon, and refine. And my refine is turned off, so it's false right now. Nothing more than that. So first thing that I'm going to do is I'm going to draw a straight line segment that would be around, let's say, 300 millimeters long. Enter. Single straight line segment, 300 mil long. And I'll just make a copy of it, you know, so that I have two of them here. Okay. Here, back in Grasshopper, I will take my whole definition and kind of move it to the right-hand side so that I have more room on the left hand to do something more fun with these curves. So the first thing that I want to do with these curves is I want to reference them in, right? So for that, I will be creating a new curve component container, CRV, curve. I'll be creating a new one, right-clicking on it, set multiple curves, and just, you know, having them in Grasshopper. The effect that I'm after is that curves should change. Like if, okay, let's do it this way. If I connect them now, you can see that, you know, this is quite boring. It's the same thickness throughout both of the curves. If they get moved closer, too close to one another, they will be joined into a surface. If I move them further out, they will be disconnected, right? So it's kind of boring. I want to have a possibility on how on changing the thickness of the curve so that it has variable of the pipe, so that it has variable thickness. And I can do that by, first of all, disconnecting my curves. So now I just have a separate component here. And to be able to change the thickness, I need to divide these curves up into small parts. And I can do that by using divide curve component, divide curve, and choosing the amount of segments that I want each curve to have. So I will choose something like 12, I don't know. Let's say 12 segments, some random number. The problem is that from this divide, what I get is whatchamacallit? I'll get there. We only get points, we get tangents, and we get parameters, right? We don't get separate line segments, which is not nice. The tool that does that is called shatter. Shatter, like break, right? So shatter a curve into segments. Super. We choose that. And it's going to ask us for two things: curve to trim, or curve to break into parts, and parameters to split at. So I will take my curves and I'll connect them to the curve input of shatter, because those are the two curves that I want to break into parts. And then for parameters, this is why we used curve divide, because it gives us parameters at which, so parameters are basically lengths, different lengths of curve, which describe you know, an area on the curve. So divide curve gives us parameters as a list, and we can connect those here into our shatter parameters. Notice how one line here that we get is dashed and the other one is not dashed. It means that parameters come in as two separate data branches, right? One for each curve, right? So two separate lists. While the curves come in as a single list with just two curves in that list. So we need to take care of that. And to do that, I will be using a tool that's called graphed tree. It's the same thing as just using graphed, only that in this case, I believe it's better to have it visually present for us. So graphed tree, or is it just graphed? No, it's graphed tree. And instead of just simply connecting curves to the shatter input, I'll be connecting curves to the tree input here, and the tree input gets connected to the shatter. And now it should be two branches here, two branches here, two branches come out from shatter. That's super. Actually, no, that's not super, because from shatter, I want to get just a single list of curves. And here I get two lists, you know, one list belonging to one of the curves and the second list belonging to the second curve. So I will just right click on the S output of shatter and choose flatten. And now it's a single list containing 24 small line segments. So every one of these is a single small line segment now. So then I can connect my shatter output to the curve input for curve charge, like this. And now this happens. Not ideal. Oops, don't do that. Don't do that. Okay, so it's not ideal, but it's starting to do something, right? At least now I know for a fact that these guys are definitely how do I say that? Just give me a second. I know for a fact that these guys are definitely separated into parts because where two parts meet, they make this kind of a bulge, which is okay. I wonder how that would act. Well, that's cool. We can make a ladder this way. But we're not here to make ladders. We're here to make some bendy lines. So, first things first. I wonder what would happen if we change this charge strength to 0.5. Oh, that's what happens? Okay. What if we change it to 2? So the bigger the charge strength, the lesser this kind of bulging will be. That's good to know. I'm just learning it as well. For now, I'll just leave the charge strengths at 1. So moving on. I want to have a control point, some sort of a attractor point. And the closer the curves are to the attractor point, the closer parts of the curves are to the attractor point, the thicker they will get. So I'll just take my attractor point, just create it in Rhino, just a point, and place it somewhere in between the two curves, somewhere here. That's fine. And I'll just grab a point. Container. I'll right click on it, set multiple points, or sorry, set one point. We only have one. Set one point, choose that one. And now this guy is set, right? So now I want these curves. Okay. Again, all of the both of these curves are divided up into smaller parts, into smaller segments, and I want to give each segment a different radius, right? Because right now we're locked to radius 10 or even less, you know, like radius 5. I want to give them bigger or smaller radius, considering how close they are to my attractor point. So I need to somehow measure distance, right? So I have my all of my segments here, like 24 curves. And I have my point here. So to work with it, I can use pull point command. And the geometry that pulls is going to be my attractor point, right? So that's going to be the geometry that is going to pull these curves towards it. That's the first part. The second part is pull point command asks me for points, but here I have curves. That's problematic. I need to get some sort of a point from these curves. And I think, like, yeah, best case scenario, not best case scenario, but the best thing to do is just to get center points from each of these curve segments. So I will just ask for point on curve. Point on curve. This tool right here, which looks like a slider. And if I connect my shatter output to the point on curve and kind of move the slider around, you can see that, you know, it basically just creates a point on the proportion of the curve. So if I right click the slider and choose middle, it's going to give me, oops, it's going to give me the middle point for each curve segment, which I can connect like so to closest. Yay. So we've done that. Now we have distances, right? And as per usual, I will show you the distances that are being measured. You don't need to do this part. This is just for me to show you. So these are the distances that are being measured, right? These lines here. All right. Let's move on. We have the distances. Let's just casually see what happens if we connect the distances to the radius instead of the static radius of 10. I delete that. And what happens if I just connect the distances from pull? Apparently it crashes. That's what happens. Oh no. No, 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 no. Oh man. No, wait. It's doing something. Why is it freaking out so much? Are the distances so big? Oh crap, I think the distances are way too big. Yeah, I messed up with that one. Time to pause the recording. Zoom recording, there we go. So instead of connecting distances straight up, because that wasn't a smart thing to do, I will be remapping the distances to reasonable numbers that can be used as the radii of my curves. So I will use remap, remap numbers node, as we did 3 times now or 2 times now. The values that I'm remapping are distances. No, you can't obtain a rectangular section. If you want a rectangular section through something, you need to use sweep, sweep 1. And then it's going to you know, so to make a rectangular section through something, then it's not cocoon, it's straight up rhino. You would need to do center like that. Something like this. Rotate. And then let's rebuild. 5. Something like this. Doesn't matter. Then you would use sweep 1. Select rail, you would select the curve. Select cross-section curves, you would select the rectangle. Okay. And it kind of sweeps then, right? In this case, it's always going to be radius based, meaning it's always going to be it's always going to be cylindrical. Moving on, remap values. Those are the distances that we're going to remap. So I just connect those like so. Then we have source domain, which is in between 0 and 1, and that's not the case. We need the minimum and maximum distance, right? So we will use bounds, and connect the distances to the bounds input and connect the bounds output to the source domain input, like so. And then we have the most important part, which is the target domain, where I can kind of either use a panel or use construct. That's not how you write construct. Construct domain, like that. You can connect it, and then I can say, okay, so the smaller the distance is, the smallest distance should be what number, right? So this distance is going to be smaller, so it should be remapped to what radius value. And I'll say, let's say 20, I don't know, 20. And then the largest distance, so somewhere here, should be remapped to what value? I'll say 1. No, I can't say 1 because here our cell size is set to be 3. So that is pure minimum of how small I can go. So I'll say 5. So the closer you are, the closer you get, the closer these curves are to this attractor point, the closer they get to having a 20 for a radius. The further they are, the thinner they get until they reach 5. And now I can connect the remapped values to my radius inputs, like so, and run the cocoon. Oh God, this looks so bad. Oh, it's so ugly. Does it work? No. Which part? The remap, you mean? The remap was plugged in instead of the radius for the curve charge. Yeah, the cocoon plugin is not a lightweight one, so to say. So like that. Still doesn't work. Does it give you an error, or is it just not completely not working? Which node gives you an error? Cocoon. What kind of error do you get? Click on the red balloon. Value too large or too small. Okay. What's your cell size value? 3. What's your domain end value? My assumption is that, where is the, yep. So where you have the remap, right? You say this, the starting domain, right? You specify that the starting domain is between the smallest and largest distance, right? And that's how we can control the distances. Yeah. So and then you have, oh yeah, I assume that works now, right? So the smallest value in this domain needs to always be like 5 or something like that. It always needs to be bigger than the cell size. If it's smaller than the cell size, why does it work for me? I mean, it's going to start breaking here, but still works for me. I don't know. Usually it's when you give it a radius that's smaller than a certain cell size. All right. So we have a wavy line. There's one thing that I want to check. Wait, let me. I forgot to resume the recording, by the way. Whoops. There we go. So with a higher cell size, it seems to be doing the trick. And the thing that I get from this is if I bake it out, you know, I get this kind of a system here, Arctic. I get this kind of a either floor system or whatever, with a few, you know, mistakes here and there, but those are possible to clean up. But yeah, that's the main goal here. That the reason why I'm showing it to you is that here it's treating like it's working like it's a surface, right? And here it's starting to work like a line, like a bunch of lines, and then continuing on here, working as a surface again, right? So you can have a lot of control over it with just a single attractor point, how close the lines are next to each other, and so on. And for instance, if I were to F10, if I were to just take some of these control points, I have no idea what's going to happen, but let's YOLO it. This was a very, very bad idea. Constantly crashing. But it is what it is. The cool thing about yeah, there we go. So that kind of works. I mean, I don't like the fact that the curvature broke. So I'm going to do one thing with it. Let me jump back here. Jump back here. There we go. So I'll quickly jump back to what I had before, right? And let me just explode and delete the center part here. And instead, I will just take these curves and move them up a little bit. And then do the blending again. Blend curve from here to here, like that, like that, like that. Mm-hmm. Like that. And let's think, what would happen if I just select these two, kind of rotate them like so, so that they're placed like so. Yeah, I can do that. So I'll just join these up, rotate them 180 degrees so that they cross each other like so. And I can simply just reference in these curves and then check how these curves will work, right? As it's going to be calculating this, this is the final thing that I wanted to show today. You know, that it all matters. What matters the most is the proximity from curve to another curve, how close the curves are to another. Because if you have just an array of curves, you can create a surface with it, which is very nice. Or if they're getting further away from each other, then it's going to be a list of just lines. Oh crap, I forgot my attractor point, which needs to be here. So then it becomes a list of lines. So there is this kind of a, not a disconnect, but transition between surface and the line in this kind of approach, or volume and the line with this kind of approach, which I really enjoy. And I think you would agree that this is a pretty, you know, interesting way to work with it, but also somewhat frustrating given the fact that this is a pretty slow, well, not that slow, but not as snappy of a process. But oh, by the way, the time that you pay waiting for this to mesh out with marching cubes is the time that you save by just checking what and seeing that this is a valid mesh and this is a closed double precision polygon mesh. Cocoon will most of the time produce a clean mesh that is straight up 3D printable. I wouldn't suggest 3D printing this one out, especially considering the fact that these are just, you know, these would be just plastic pipes that would break off immediately. But, you know, with certain precautions, with certain amount of joinery, such as this, I think it's definitely doable. So now it's time for questions. Do you have any? Either through chat or through the microphone. So now I'm recording it. Thankfully, all we did was just create a curve here. Nice. Thanks for reminding. Where were we? Fillet, right? So my fillet radius right now is set to be 2, and I can see from the grid that 2 is a pretty heavy fillet for this kind of the size of a shape. So I'll just change my fillet radius to something like 0.5, enter. So now my radius is 0.5, and I will just click on the arc and click on the base line here. So it rounds it off. And I'll repeat the fillet command for the other part, other side, like this. So it's rounded off, right? That's the shape that I have. Now, once I have it, I will go to perspective view and just rotate it 90 degrees, move it slightly up so that it's kind of vertical. And I will just extrude it, extrude curve. I'll change this to shaded view just so that you can see, whoa, what's going on there? That's strange. Anyway, I'm just extruding it, and I will choose the extrusion distance, which is going to be, so if this is 10, I think if my extrusion distance is something around 100, well, let's do 150. Yeah, something like that. That seems okay. Okay. So I have my single weird cylinder thing here. Works for everyone? If your cylinder, I lost you at NURBS curve. Before the fillet or what? Wait, lagging. Ah, okay. So the NURBS curve tool is this one right here. Right next to the polyline tool, you have control point curve tool, and it makes a NURBS curve, but it's called a control point curve. So you just use this tool right here, and just kind of follow through counterclockwise through the rectangle points and just make an upside down U shape. Then you use close curve to close it off. Then you use fillet and round off those kind of sharp seams. Rotate the NURBS curve, and then just use extrude curve. If you're using extrude curve and it's not creating a cap, no. Well, you can do it, but like if you have a rectangle and you want to make it into a NURBS curve, you just rebuild it, and you just choose degree of 3 and point count, let's see, 4 as well. But then it's just going to be an egg, right? Every rectangle becomes an egg. Some of you might see that the extrusion that you've done is hollow, meaning it doesn't have a surface on both sides of the extrusion. You can either, as you're using extrude curve command, you can, wait. Let me go back, extrude curve. Then you can choose solid to be turned on, and then it is going to cap the ends of the pipe, of the extrusion, sorry. Or you can, if solid is turned off and you do the extrusion either way, then you can just choose this form and type in cap, and it's going to fill in the ends here. You can do more things with it, such as fillet edge, radius 0.5, and just choose the ends. Ooh, if this happens, that means that the radius is too big. Then we need to do like 0.2 and fillet the edge here, right? To kind of round it off, but this is unnecessary for this tutorial. So we have this pipe, and it's a closed, well, if we type in what, it's a closed solid polysurface, valid polysurface. I can take this pipe and holding down the Alt key, I can copy it to the side by 10 units, because I know, I've started with a 10 unit rectangle, 10 by 5 rectangle. So I know that if I copy this pipe, this extrusion sideways by 10, it's going to kind of align. These copies are going to align. And instead of copying, I want to make like, I don't know, 50 of these. So instead of copying, I will use array tool, enter. And I'll say number in X direction. So X direction is the red arrow, Y direction is the green arrow, and Z direction is the blue arrow, right? So number in X direction, I will just say 50, enter. Number in Y direction, 1 is fine. Number in Z direction, 1. And then X spacing, I will just type in 10. Hit enter, enter again, and I've just made 50 of these. Works? Okay. So we have 50 copies of this bad boy here. Missed it? Okay. The array part? Which part? Okay. Delete. Select the shape. Array. Enter. Then for number in X direction, you choose like 50. Well, it depends what direction you're going to be copying it in, right? In my case, I want to copy it along the red arrow, right, to the right side. So it's going to be my X direction. In your case, it might be Y. It's not going to be Z, but it might be Y. But here I just choose number 50. So I'll make 50 copies. Then it asks me how many copies do I want to make in Y direction. I will just keep it as 1. And how many copies do I want to make in Z direction? I'll keep it as 1 again. And then once I've done setting up that, it's going to ask me what's the X spacing. So what's the distance between every copy that it's going to make? And I know that the distance needs to be 10. So I'll just type in 10, hit enter, and hit enter again. And then I have all of my shapes in a line here. So now these are, okay, I guess, shapes like shapes. But what if I want to change the form of them, right? Should I remodel all of them, individually, or is there a tool that does that? And there is actually a tool that does that. And that tool is called, let me jump back, by the way, to top view. That tool is called Cage Edit. Cage Edit. So I select all of my shapes and I type in Cage Edit, hit enter. And then it asks me, would I like to select some sort of a control object, or would I like to use a bounding box, a line, a rectangle, or whatever? I'll choose bounding box. So when it asks me to select the control object, I'll choose bounding box. It's going to ask me what's the coordinate system, and I always use world. So I just hit enter. And it's going to ask me for cage parameters. X point count, Y point count, Z point count, and degrees. So we don't mess with the degrees. We always have them set to be 3. That's fine. But we will be messing around with the with these X, Y, and Z point counts. It's much easier for me to first set it up and then explain what we did, rather than explain it without you actually visually seeing what we're planning to do. So let me just set it up. For Z point count, since I'm not going to be messing around with the height of this shape, I will click on the Z point count. I'll choose 1, right? Oh, sorry, I'll choose 2. 2. Z point count 2. Then Y point count. This is how many control points it's going to have along the Y direction. I'll choose around, I don't know, let's try 8. Maybe not 8. Let's try 6 for now. 6 control points for Y, and X point count, I will choose, if we have, let's do 20. So X point count 20, Y 6, Z 2. And then degrees are all 3, except for Z, the degree changed to 1, but we don't care about it. Then I hit enter. Oh yeah. Region to edit, we don't care. We just hit enter again until it stops asking us questions. So what we get from it is we get this kind of a, maybe it's better to see in perspective, we get this cage of control points, right? And then back in the top view, I will just choose all of the control points that are that are in the middle, like the middle row of the control points. I'll choose that row. And for now, just to show you what it will do, let's just move those control points just slightly to the left. And let's look at it from, let's look at it in perspective view. See how all of this deforms along the control points, right? So cage edit, and let's Control Z, let's undo. So cage edit lets us change the structure according to this kind of a cage and its control points. So if you change the control points of the surrounding cage of the structure of the form, it will change the form within that bounding box. So what I can do with it is, for instance, I can unselect some parts, some control points on the left-hand side. I can unselect some control points on the right-hand side, and I can only mess around with the control points that are here in the middle. And I can just slightly move them. Don't be very brutal with this tool, but you can slightly move them to the side. And then in, for instance, right view, I can move them slightly up. Again, not by a lot, just a little bit up, like that. If I were to hit escape again, the control points are going to be gone. And now you can see, you know, what kind of a form we have made. Let me change this to Arctic view so that it's easier to see. Got it? Okay. So you can use this method of cage edit to twist and turn any form that you want. The problem is that, first of all, it's a little bit heavy, as you might have noticed by now. It's a little bit on the heavy side when it comes down to computation speed. And also, it introduces a lot of additional information into these surfaces. But I believe that is fine. So this is actually a sole of the shoe. If I were to see how I tricked you, and now we're modeling out the shoe. If I were to turn this around, this is the bottom of a sneaker shoe. Then we would just need to trim out the foot, like a foot outline, and you would have the bottom of the sneaker. It's all geometry. It doesn't matter if it's a shoe or a building. So that's that. Don't need this anymore. Just to kind of show it as another example, I'll just have this box here, and I will just, and this one you don't need to follow. This is just to lock the example in place for you. Boolean union. I'll just join these guys up, and I'll use cage edit for them. Again, I'll choose bounding box. I'll choose world coordinate system, X point count. This time I'll just choose something like 4 in X direction, 4 in Y direction, 4 in Z direction, and Z degree I will choose to be 3. So degrees are always 3, unless you're using just 2 points for the one of these counts. So 4, 4, 4, 3, 3, 3, enter, enter. We have the control points, and let me just grab, I don't know, let's say this guy right here, just move it. See? Distorts. Which means I can kind of start messing around with it a little bit. Kind of distorting this box. Not this box, but this form, bit by bit. Right. I'm just trying to make an apple. Okay. So that's that. The thing is that once we're done, right, and I hit escape a bunch of times, then this is the form that you have, right? There's no real way of how to get back to the form, and unless you just do Control Z, you know, to undo the cage edit tool. But let's say I want to change this form even more. Notice how cage edit left me with this curve, like curve group. And if I select it, it says one control added to selection. So I know that this is something else. This is not a bunch of curves. This is, you know, it has more information than just curves. This is something that can be reused, meaning that if I want to change this form again, I can use cage edit, select captive objects. I select these guys here, enter, and then I can, for control object, I can select these curves which were made by the first time we used the cage edit tool. So I can select these. I just clicked on them and it immediately started asking me other questions. So I can click here and we're back to, you know, to editing this. So I can continue editing, right? If you delete the control and you kind of do something else with the shape and so on, then that information is gone and you won't be able to use cage edit. At least you won't be able to use cage edit with those control points anymore. You will be, though, be able to use cage edit again. That's not that. Cage edit. You will be able to use it again. Come on. Cage edit. Bounding box. World. Yes, yes. But the problem will be that the box is not going to be distorted, right? So you will need to kind of continue playing with a new box, which might be a little bit tricky. Cool. Okay, that's good. So that is one strong tool to use, but also with great power comes great responsibility. That tool can you can lose control. you can lose control with that tool pretty fast. So be mindful of you know how you use it and for what reason you're using that tool. There is one more thing that I want to show you, and we'll finish for now for today because my voice is completely gone. Come on. And that tool is edge surface. Block edit. What do you mean block edit? We don't have any blocks. Okay, block edit, sure. This box and this cylinder is, I will make them into a block by just typing in block, enter, block base point. I will just choose some point on here and I'll name it block plus cylinder. Hit OK. So now if I select it, it says one block instance selected, which means I can kind of, if I copy it multiple times like that, these are not necessarily copies, but these guys are, well, they are copies, but they reference the same geometry, meaning that it's quite similar to V-Ray proxy, right? So if I were to type in block edit now, by selecting one of them, I can, wait, what, this is a new, oh crap, I can only, this is so stupid. Yeah, I escape. I can only add or remove objects. Before you could change stuff with these blocks, but apparently you can't anymore. So let me change this a little bit. So back to here, right? These four are all blocks which reference the same the same original block, which is called box plus cylinder. And then I can add, let's say, a sphere here to this one and use block edit. I'll just choose this block and I can add object and I can choose the sphere, enter, hit OK. And now all of these will also receive that sphere, right? So I can change multiple instances of the same thing through blocks. You can scale copies and you can rotate them, and all of these Cartesian transformations apply. I believe. Okay, CageEdit doesn't work. I hope that CageEdit works. Grasshopper will hate it. Grasshopper doesn't like blocks at all. Boolean operations hate it. What else? Trimming operations hate the blocks. But these guys are really good for copying trees and stuff like that. Can you edit the copies with CageEdit? No, you can't. All you can do with blocks is basically move them, rotate them, and scale them. And you can't use Boolean operations with them as well. If you want to get rid of the block, let's say you have the, all of these copies here, and you want this copy to not be a block, all you need to do is just type in explode. And now these are back to being three different objects. All right. So those are blocks. Honestly, I do use blocks, but I use them only for technical projects. When I'm sketching or when I'm doing like competition entries, I never use blocks unless it's something that Yeah, I do use blocks for trees. If I need to create a tree and kind of make a forest out of it, I will make it into a block, just so that it's faster for Rhino to kind of calculate it. But other than that, it's very useful for technical projects for sure. Renderings, blocks for renderings. So yeah, that's what I mean by adding trees. Getting the same material for pillar. No, for that I would just have a separate layer. Instead of using blocks, I would have all of the pillars in a separate layer, and I would just call them, concrete pillars. And then I would just use right-click, select objects, and select the pillars, apply the layer to them. For that, I wouldn't use blocks. Unless I would be definitely sure that I will not be changing the geometry anymore. But even then, no reason. For that, no reason to use blocks. It's mostly just for convenience of copying the same thing many times. All right, so that's blocks. Short tutorial on them. The last one that I want to show is called edge surface from 2, 3, or 4 edge curves. And I have already shown this during the Rhino course, during your second year of studies. But this one might be a little bit more, a little bit nicer in your case for this project, because you can see benefit of surface from 4 edge curves with your current project here. So for instance, how do I show it to you? Let's say you have a surface here, and you have another one here, and you have some sort of a curve here, curve here. You don't need to follow this. This is just to quickly show. So you have 2 curves. I'll just rebuild them. Point count 4, that's fine. I'll just mess around with the control points of these curves. Something like this, something like that. Extrude curve. Oop. Extrude curve. Yeah, sure. Just flip this. So I have this kind of setup going on, right? For some reason, there's a hole here that I didn't think of on how to kind of fill it in. As long as the hole has 2, 3, or 4 edges like this, I can use this surface from 2, 3, or 4 edge curves to fill it in, right? And this is something that I constantly use when I need to make sure that the object is doesn't have any openings, doesn't have any holes in it. This is, I call it stitching. This is something that I use to stitch the geometry back into a single surface. So this guy right here, if I choose it, it will ask me to select the curves, and then I don't even need to create the curves. I can just click on the edges, this edge, this edge, this edge, and this edge, and it will just create a surface that fits perfectly in between these 4 surfaces here. Then I can join all of those up, and this is, as you can see, one single polysurface, open polysurface. EMAP will show that there are indeed, it's not seamless. I mean, it's not tangent based. For instance, if I had a surface here and let me just copy it, move it here, and kind of rotate it. Let's say if I were to connect these 2 surfaces by using blend srf, like that. Okay, flip this one, join, and use emap on this one. You can see that the connection between these is seamless, right? In this case, it won't produce a seamless connection, but it will produce a connection between 4 surfaces rather than just 2. So it's nice. Oh, this one, blend SRF, blend surfaces. And you just choose the 2 edges that you want to blend together. We have less than a minute left, so I'll finish up for today. If you have any additional questions, just write them in the chat and I will answer them there. Cool? Take care, guys, and keep doing what you're doing. Never stop, never stopping.